Welcome to the Snoozy Scientist, a calm corner of the universe where curiosity and science drift together to put you to a calm sleep. Tonight, we're traveling back more than 600 million years to a world that had just broken free from its most brutal prison. For tens of millions of years, Earth was locked in ice. Glaciers stretched from pole to pole, sealing oceans beneath miles of ice. The equator itself, usually the warm heart of the planet, lay buried in white silence. Scientists call this Snowball Earth, an age when the world plunged into unimaginable cold, with temperatures falling far below freezing, creating the longest and coldest ice age the world has ever known. And then, one day, everything changed. The greenhouse gases that had been trapped for ages suddenly surged into the skies. At the same time, volcanoes rumbled beneath the frozen crust. When they erupted in fire and ash, the ice began to melt. Oceans, once hidden beneath ice, began to boil with strange colors. Waters ran green with iron, red with rust, and black with ash from erupting volcanoes. The thaw unleashed a flood unlike anything in Earth's history, seas swelling higher and higher until whole continents vanished beneath them. The skies were not the calm blue we know, but a hazy ceiling of storms, thick with carbon dioxide and vapor. Lightning split the clouds, thunder shook the air. This was Earth's strangest age, a time when our planet felt more alien than familiar. On land, there was no life to soften the world. No trees, no grass, not even the smallest moss. Only barren rock, scarred by torrents of meltwater, with shallow seas creeping over the edges of silent continents. But how did life survive the planet's most brutal prison? What did the landscape truly look like in the aftermath of these floods? What kinds of creatures crept into existence here? And why did nearly all of them vanish before the Cambrian Explosion? Tonight, we'll step softly into this forgotten flood world to uncover how our planet was reborn from ice, how the first alien creatures flourished, and what lessons this hidden age still holds for us today. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's distant past, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little corner of the internet grow. I do hope this story soothes you toward rest. Now, let's step softly into the forgotten age when Earth was reborn from ice and flood. When the grip of ice finally loosened, Earth began to move again. What had been a silent marble sealed in white was transformed into a world of water in motion. Glaciers that had stretched for thousands of miles melted into torrents that poured across the continents, carving deep valleys and sending walls of water rushing toward the seas. These floods were not like the floods we imagine today. They were global in scale, reshaping coastlines and drowning entire landscapes that had once lain locked beneath frozen sheets. As the ice retreated, sea levels began to climb. Every meltwater stream, every collapsing glacier added to the rising tide. Over time, the oceans swelled so high that they crept inland, swallowing great expanses of continental crust. Vast areas of land that had stood exposed during the frozen age disappeared beneath shallow seas. What had once been bare rock covered by ice became coastal plains, deltas, and marine basins. The outlines of the continents shifted dramatically, leaving scars that geologists can still trace in stone. The scale of this rise is difficult to picture. Imagine shorelines that extended for hundreds of miles, suddenly falling to the advance of seawater. Imagine valleys that once lay beneath thick ice, becoming fjords and flooded troughs. The weight of the glaciers had pressed down on the continents for millions of years, and when they melted, the land rebounded unevenly. Some regions rose, others sank, creating networks of new basins ready to be filled with water. The balance between ice and ocean tilted sharply, and the Earth entered one of its wettest and most unstable chapters. Evidence of this planetary flood can be found in the rocks beneath our feet. In some places, glacial deposits known as tillites still cling to the ancient crust. These are poorly sorted mixtures of stones and sediments left behind by retreating glaciers. They form a geological fingerprint of ice once present, even in regions that today lie near the equator. The fact that such deposits exist in tropical zones is one of the strongest pieces of evidence that ice once reached across the globe. Other traces lie in the form of drop stones. These are isolated boulders found in fine layered sediments, dropped into the sea when melting icebergs released the rocks they had carried. Each dropstone is like a frozen memory of icebergs drifting across oceans that once reached the tropics, leaving behind their cargo as they melted. Scattered across ancient seabeds, these stones show us that glaciers had indeed reached the sea and that the thaw was powerful enough to release them into distant waters. The marks of rushing floods are also preserved in erosion scars. In many regions, you can find grooves carved deep into bedrock, channels etched by the violent torrents that poured from melting ice sheets. These grooves often run in parallel lines, pointing in the direction the ice once flowed. Their size and depth reveal the enormous force of water moving across the land. Some are so large that entire rivers could have flowed through them, yet they formed in a geological instant when the ice collapsed. As oceans rose, the chemistry of the seas began to shift. The sudden influx of fresh water changed circulation patterns, and the sheer volume of water flooding in created unstable layers in the ocean. Nutrients locked away in ice were delivered to the seas, setting the stage for blooms of microbial life. At the same time, the sediments washed from the land carried minerals that would change the color and chemistry of shallow waters. What had once been a frozen desert was turning into a world dominated by restless seas. The Earth of this time would have looked unfamiliar to us. Mountain ranges that had once been buried in ice stood exposed, their slopes cut by glacial erosion and polished by meltwater streams. Valleys filled with rising seas became long, narrow inlets. Plains that had been locked beneath kilometers of ice were suddenly drowned beneath shallow coastal waters. From the perspective of the life that clung to survival, the planet must have seemed immense and unstable, every shoreline shifting, every horizon altered by water. It is important to remember that this transformation did not happen in a single day. It unfolded over thousands of years, but on a geological scale, it was abrupt and cataclysmic. Continents that had been frozen in silence for tens of millions of years were quickly reshaped, and the oceans claimed vast new territory. Earth was no longer a snowball, but it was not yet the stable planet we know. It was something different altogether, a water world in flux, restless and strange. And as the seas continued to rise and spread across the continents, something remarkable began to unfold within them. The chemistry of these newborn oceans was not what we know today. They carried the stains of minerals, the marks of volcanic ash, and the nutrients of a planet reborn. In their shifting colors and restless tides lay the foundation for an alien ocean world that was only just beginning to awaken. As the seas continued to spread across the continents, they did not look anything like the familiar blue waters of today. These newborn oceans carried the chemical fingerprints of a planet that had just broken free from ice. The melt had poured vast amounts of minerals and sediments into the sea, and volcanic eruptions added yet more material to the water. What followed was a transformation that turned Earth's oceans into something alien, a world of shifting colors and restless chemistry. Iron was one of the most important players in this strange scene. For millions of years, as glaciers had covered the continents, rivers and rainfall had been almost entirely cut off. Without fresh inputs of oxygen, the oceans beneath the ice remained low in oxygen and rich in dissolved iron. When the thaw came, oxygen returned to the seas, delivered both by the atmosphere and by the resurgence of photosynthetic microbes. As the oxygen mixed with the waters, it reacted with the iron, and the oceans turned red with rust. This process can still be seen on a much smaller scale today. When iron meets oxygen, it oxidizes and forms reddish particles that sink to the seafloor. In Earth's deep past, this reaction created vast layers of iron-rich rocks called banded iron formations. During the post-glacial world, the seas must have shifted into vivid shades of crimson and brown, the color of oxidizing iron spreading through shallow waters. To any living creature, the seas would have seemed unsettling, as though the planet itself was bleeding into the ocean. But the story of color did not end there. The floodwaters brought with them phosphorus and other nutrients that had been locked in ice or trapped in rocks. When these nutrients entered the seas, they fueled explosions of microbial growth. Algae and cyanobacteria thrived in this new environment, their populations swelling to levels the planet had not seen for millions of years. The surface of the oceans bloomed with life so small it could not be seen individually, yet in such numbers that it stained the water green. Algal blooms today can be seen from satellites, spreading across modern seas like great emerald patches. In the ancient world, they may have been even more intense. Picture oceans not of clear blue, but of cloudy, luminous green, stretching to every horizon. The color was not stable either. As blooms grew and died, they changed the chemistry of the water again, releasing organic matter and altering oxygen levels. These cycles must have been wild and unstable, giving the seas a restless quality that made them feel alive in their own right. The combination of red iron and green algae meant that Earth's oceans were more colorful than at any other time in history. Imagine sailing over waters that shifted from rust-colored shallows to vast green tides, with patches of dark, almost black water where volcanic ash had mixed into the seas. The surface would have been mottled, streaked, and ever-changing, reflecting a planet in the middle of violent transformation. The chemistry of these seas also carried consequences for life. Oxygen was beginning to rise, but not everywhere at once. In some places, oxygen was plentiful enough to allow larger organisms to emerge, while in deeper waters, it could still vanish quickly. Microbial mats along the seafloor thrived in these conditions, feeding on nutrients stirred up by tides and currents. Cyanobacteria released oxygen as a byproduct of photosynthesis, slowly enriching the upper layers of the ocean. This tug of war between oxygen production and oxygen depletion defined the character of these alien seas. Geologists studying ancient rocks can still find evidence of this chemical turbulence. Layers of sediments show alternating signs of oxygen-rich and oxygen-poor conditions, recording the unstable dance between life, nutrients, and the elements. Some layers are stained with iron, the mark of oxidation, while others contain sulfur compounds that hint at oxygen-free waters. The record suggests a world in flux, where chemistry could swing from one extreme to another in relatively short spans of time. For the life that floated within these waters, stability was rare. Microbes adapted quickly to shifting conditions, taking advantage of each surge of nutrients. Populations of algae might have exploded in one season, only to collapse the next when oxygen dropped or when minerals were consumed. These cycles of bloom and bust were part of the reason life remained simple for so long, Yet they also laid the groundwork for more complex forms to one day emerge. If one could have stood on the shore of this ancient world, the sight would have been disorienting. Instead of a horizon of calm blue, the seas would have rolled in deep shades of green and red, their surfaces thick with microscopic life and minerals reacting with the air. Every tide, every storm, and every current would have stirred this mixture into new patterns, giving the impression of a living ocean in constant motion. The world after the ice was not only drowned, it was painted in colors that made it seem almost otherworldly. And as these alien waters churned with rust and blooms of green, the skies above were undergoing transformations of their own, filled with storms, lightning, and the smoke of volcanic fire. Above the strange seas of red and green, the skies told a story just as alien. The end of the ice did not bring calm. Instead, the atmosphere grew heavy and unstable, filled with the restless energy of a planet trying to find balance after millions of years of silence. The release of greenhouse gases during the thaw had trapped enormous amounts of heat, and the warming surface waters of the ocean added yet more energy to the air. This created a world where storms were constant companions. Clouds towered higher than mountains, their edges glowing white in the sunlight, while their bellies churned with darkness. They gathered moisture from the newly freed oceans and released it in sheets of rain that battered the barren continents. Lightning stitched across these clouds in blinding streaks. With oxygen now returning to the skies, electric discharges could crack through the air with incredible force, illuminating the landscape for miles around. Each strike must have echoed like a drumbeat across empty valleys, rumbling against the cliffs left behind by retreating glaciers. The storms rolled on without interruption, forming and dissolving in an endless cycle of heat, water, and pressure. Hurricanes swept across the seas with a strength that is difficult to imagine today. The difference in temperature between the cold meltwater and the warmer equatorial regions fueled storms that could span entire oceans. Winds would have howled across the waves, driving them into walls of water that broke upon the shorelines of the continents. Without forests to break their force, these winds tore across naked rock, carrying fine dust and volcanic ash far into the atmosphere. The air itself was thick and hazy, loaded with water vapor and carbon dioxide. It carried not the clear blue of modern skies, but a dim, muted light that filtered through layers of cloud and smoke. This haze was amplified by the frequent eruptions that scarred the surface of the planet. Volcanoes, long pressed under the weight of ice, had surged back into activity once the frozen crust above them melted away. Their eruptions filled the air with ash, sulfur, and dust, darkening the skies even further. Volcanic plumes climbed into the upper atmosphere, spreading like ink in water. They blocked sunlight, cooling some regions even as greenhouse gases trapped heat elsewhere. The result was a world of extremes, where one region could be smothered in darkness, while another sweltered under humid skies. Each eruption reshaped the balance of the air, and together they gave the sky a restless and unpredictable character. Ash and aerosols from these eruptions also mingled with storm clouds. Rainfall carried the particles back to the surface, staining rivers and lakes, while lightning strikes flashed within the clouds of smoke and vapor. The atmosphere itself seemed alive, charged with static, shifting with the winds, filled with the fiery breath of volcanoes. To stand on the surface during this time would have been overwhelming. The horizon was rarely clear. Instead, it was painted with shifting grays and reds, the colors of ash and fire mixed with sunlight diffused through clouds. The roar of thunder was constant, and the air carried the sharp scent of sulfur and ozone. Rain fell in torrents, carving new channels into rock, while hail and lightning battered the seas. This chaos was not without purpose. The constant storms helped to mix the oceans, driving nutrients through the water columns and spreading volcanic minerals across vast distances. Rain delivered new elements into the seas, feeding the cycles of life that were beginning to take hold. The same violence that made the skies terrifying also gave the oceans what they needed to nurture the first complex ecosystems. The planet itself seemed caught between fire and water, its surface pounded by storms, while its depths roared with molten rock. This was Earth in transition, a world neither frozen nor stable, but something strange and temporary. The atmosphere, charged with lightning and heavy with ash, was a mirror of the turbulence below, and as storms tore across the continents and volcanoes painted the skies, the land itself began to reveal its new face. What emerged beneath the haze was not a world lush with life, but one stripped bare, a barren expanse waiting for the first signs of recovery. As the atmosphere swirled with storms and lightning, the ground below carried its own restlessness. Beneath the thinning crust of ice, Earth's buried fire was awakening. Volcanoes that had been sealed under the weight of glaciers for millions of years began to break free. When the ice finally melted, the pressure that had once held them down vanished, and magma surged upward with violent force. Lava spilled across barren continents in glowing rivers. It spread over the scarred bedrock, left behind by retreating ice, filling valleys and cracks, covering the landscape in fresh layers of basalt. Where water met these flows, steam erupted in sudden bursts, rising into the already heavy skies. The heat from the lava created pockets of warmth in an otherwise unstable world, yet the land was still far too harsh for plants or animals to claim it. These eruptions were not gentle. They were massive events, the kind that shook entire regions at once. Ash exploded into the air, billowing in clouds that reached high into the stratosphere. The skies, already dimmed by storms, grew darker still. In some places, daylight must have been reduced to a faint red glow, filtered through veils of volcanic dust. Ash settled back to the surface in thick blankets, coating rock, rivers, and seas. Every eruption added new layers of this fine material, building a geological record that scientists can still trace today. Volcanoes are more than fire and smoke. They are also engines of climate. With each eruption, enormous amounts of carbon dioxide were released into the air. This gas had been stored deep within the mantle, hidden from the surface for eons. Now, with the crust fractured and the glaciers gone, it poured out in pulses that changed the balance of the atmosphere. The release of carbon dioxide trapped more heat, intensifying the greenhouse effect that had already begun during the thaw. This surge of gases helped to ensure that Earth would not slip back into its icy prison. Without them, the planet might have frozen once again, as sunlight reflected from the still expansive sheets of white. Instead, the volcanic pulses tipped the balance toward warmth, locking the Earth into a new trajectory. The planet was moving into an age of greater stability, though the process would take millions of years to settle. For life, the influence of these eruptions was complex. On one hand, the darkened skies reduced the amount of sunlight reaching the surface, challenging photosynthetic organisms in the seas. On the other hand, the minerals carried by volcanic ash enriched the oceans, feeding the cycles of nutrients that sustained microbial growth. Iron, phosphorus, and other elements rained into the water, sparking bursts of productivity in places where the chemistry allowed it. The presence of volcanic islands also shaped the environment. As lava cooled and hardened, it created new landforms that jutted above the seas. These young islands provided surfaces where microbial mats could anchor, adding tiny pockets of life to the barren world. They also altered ocean currents, redirecting flows of warm and cold water, stirring nutrients into circulation. In this way, even destruction carried the seeds of renewal. The noise of the earth at this time must have been constant. The roar of ash columns collapsing, the hiss of lava pouring into water, the rumbles of magma chambers deep below. All of these sounds echoed across empty continents. The air carried the acrid scent of sulfur, while the ground trembled with aftershocks. It was a planet speaking in fire, reshaping its surface in preparation for the life that would one day take hold. Scientists studying ancient rocks find chemical traces of these events. Layers rich in volcanic ash can be seen sandwiched between sediments, marking the intervals of eruption. Isotopic signatures in carbon and sulfur reveal how the atmosphere was altered by each pulse of gases. These clues, locked in stone, allow us to reconstruct the scale of the eruptions and their role in warming the planet. The combination of storms above and fire below created a world unlike any that has existed since. Skies were often hidden behind curtains of dust and clouds. The seas boiled with chemical change. The continents were sheathed in fresh volcanic crust. This was a planet not only recovering from its long freeze, but also reinventing itself, reshaping its surface and atmosphere in ways that would ripple through deep time. And as the lava cooled and ash settled, the continents revealed themselves in stark silence. They were barren expanses, lifeless and harsh, waiting for the first signs of recovery to spread across their surfaces. When the eruption settled and the last plumes of ash drifted across the horizon, the continents lay revealed in silence. Their surfaces were raw and scarred, shaped by the weight of glaciers and the torrents of meltwater that had poured across them. The floods had stripped away soils, leaving behind bare stone, polished smooth in some places and gouged deep in others. Across these vast landscapes, not a single blade of grass, not a single tree broke the monotony. The continents were harsh and lifeless, their air hot and heavy, their skies dim with haze. Without vegetation to soften them, the rocks baked in the sunlight during the day and cooled sharply at night, creating an endless cycle of expansion and contraction that fractured their surfaces into shards and dust. Wind swept freely across these plains, lifting fine particles of ash and sand and carrying them far from their source. There were no roots to hold the ground in place, no forests to break the force of storms. The land was exposed to every element without protection. The landscapes themselves were strange to the eye. Valleys carved by ancient ice lay empty, their walls rising steep and sharp. Cliffs bore the marks of glaciers that had dragged across them, deep grooves pointing like arrows in the direction the ice had once flowed. Boulders, carried for hundreds of miles by rivers of ice, rested in places where no local rock matched them, dropped like forgotten luggage when the glaciers collapsed. These erratic stones remain as reminders of how far the ice had reached, silent markers of a frozen world now gone. Along the coasts, where oceans had invaded the continents, new shorelines formed. Waves beat against naked rock, cutting it into jagged edges and pounding cliffs into rubble. Without the cushioning presence of coastal plants or coral reefs, erosion was relentless. The seas advanced, retreated, and surged again, reshaping the margins of the continents with every tide. The water was rich in nutrients, but the land it touched remained empty of larger life. The only signs of life were microscopic. Along damp surfaces where waves lapped at stone, thin microbial crusts began to spread. These mats of bacteria clung to the edges of shorelines, weaving themselves into films that could survive the constant wash of water. They trapped dust and particles, forming slim layers that gave a hint of color to otherwise gray and black landscapes. Their presence was fragile, yet they were the pioneers, the first to claim a foothold on barren ground. Farther inland, where floods had receded, the land was even more desolate. Plains stretched for miles, covered in cracked lava or scoured stone. In low-lying regions, shallow pools collected, their waters stained by minerals leached from volcanic rock. These pools may have shimmered in colors of orange, green, or white, depending on the chemistry within them, creating oases of vivid hues that only microbes could exploit. They were not welcoming to larger forms of life, but for single-celled organisms, they offered tiny worlds to inhabit. Mountains, too, stood exposed. Their peaks, once buried in ice, now towered above the continents, jagged and raw. Streams ran down their slopes, carrying sediments toward the seas. In some places, these sediments collected in basins, creating new layers of mudstone and sandstone that would one day preserve the impressions of the strange creatures soon to appear in the oceans. But for now, the mountains and valleys echoed with emptiness. The air over these continents was dry in many places, despite the storms that circled the globe. Rain fell in bursts, but without vegetation to hold it, water quickly drained away, leaving behind only dust and fractured stone. Lightning strikes sometimes scorched the surface, igniting nothing, for there was nothing to burn. Fires, which would one day shape ecosystems, had not yet been born on Earth. To imagine walking across these continents would be to step into a world stripped of all the familiar signs of life. There were no sounds of insects, no rustling of leaves, no birds to pierce the air with song. The only noises were the howling of wind, the crash of waves against cliffs, and the distant thunder of volcanic eruptions. It was a silence broken only by the voice of the planet itself. Even in their barrenness, the continents played a role in shaping what was to come. The minerals locked within their rocks were slowly released by wind and water, carried into the seas, where they became fuel for microscopic life. The scars left by glaciers and floods recorded a history that would remain etched into the stone. These silent lands, hostile and unyielding, were not wasted spaces. They were the waiting stage, the foundation upon which life's next steps would unfold. And while the continents lay quiet and barren, the oceans beside them moved to a different rhythm. Their tides were stronger than they are today, for the moon was closer to Earth, pulling at the waters with greater force. Beside the barren continents, the oceans stirred under an ancient influence. High above the haze of volcanic ash and storm clouds, the moon cast its light across the waters. Yet this was not the moon we know today. It loomed larger in the sky, closer to Earth by tens of thousands of miles. Its gravitational pull was stronger, and its influence over the seas was immense. The tides of this time were far more powerful than those we see now. Waves rolled inland with greater reach, flooding shallow basins, and then retreating to expose them again. The rhythm of advance and withdrawal was constant, reshaping shorelines in ways that left lasting marks. Pools filled and emptied, sediments were stirred and carried, and nutrients were swept into new places. The tides did not simply wash against the continents, they sculpted them. Each surge of water brought fresh movement to the shallow seas. Minerals carried by streams from the land were drawn into circulation, mixed with volcanic ash and dissolved elements. As the tides retreated, they left behind pools that shimmered with strange colors, enriched with nutrients, but cut off from the wider ocean. These tidal pools became tiny laboratories where chemistry and life could mingle in unique ways. The constant pulsing of the tides meant no pool remained the same for long. Each cycle refreshed them, each surge altered their chemistry, creating an endless variety of conditions. For the microbes that had begun to spread along the coasts, this was both a challenge and an opportunity. The tides overturned sediments, burying some organisms while exposing others. They delivered new supplies of nutrients, then withdrew and left them in concentrated pools where growth could accelerate. Cyanobacteria, already thriving in the seas, spread into these environments, forming mats along the edges of the shore. Their filaments trapped sediments, creating slim, layered structures that grew with each tidal cycle. These mats left faint traces in ancient rocks, recording their presence in rippled textures that can still be seen today. The tides also stirred oxygen into shallow waters, helping to sustain the fragile balance of the seas. Photosynthetic microbes released oxygen into the air, but the mixing of water by tides ensured that this gas did not remain in one place. It spread through currents and waves, supporting larger microbial communities. Though life remained microscopic, it was beginning to find a rhythm shaped by the moon's pull. The daily rise and fall of water created a tempo that organisms could follow. Growth surged when tides delivered nutrients, then slowed when waters retreated. Layers of microbial mats built up in sync with these cycles, much like tree rings that record the passing of seasons. Even in this early world, life was tied to the turning of celestial bodies. The closeness of the moon gave these rhythms a strength and intensity that shaped entire coastlines. The strength of the tides also influenced the chemistry of the oceans themselves. As waves crashed and retreated, they helped to keep nutrients in circulation. Iron and other minerals, released by erosion on land and by volcanic eruptions, were mixed into the shallow seas. Without this constant stirring, the oceans might have stratified into layers, with oxygen trapped at the surface and deeper waters deprived of it. Instead, the tides ensured that the seas remained restless, mixing oxygen and nutrients across wide areas. Imagine standing on the shore of such a world. The moon would rise huge and luminous in the sky, casting pale light across waters that shifted from green to red to black. The tide would roar as it surged inward, filling shallow basins with foaming water, then recede with equal force, pulling stones and sediments back into the sea. This cycle repeated endlessly, a heartbeat that pulsed across the planet, linking the oceans to the heavens. The influence of the moon was not only physical, it set the stage for the patterns of life itself. In time, larger organisms would come to rely on these cycles, timing their movements, feeding, and reproduction with the tides. In this early world, the first hints of that connection were already present. The microbes that clung to rocks and shorelines grew and spread in tune with the rhythms of the sea, responding to the cosmic pull that guided their world. The continents may have been barren, but along their edges, the dance of tides was already shaping ecosystems. The moon's closeness created a world of motion, a world where every shoreline was restless and where life was bound to the ceaseless rhythm of water rising and falling. And as the tides churned and reshaped the coasts, the oceans themselves were becoming richer, filling with nutrients and oxygen, preparing to support new forms of life that would soon stir beneath the waves. With the tides surging under the pull of a closer moon, the stage was set for life to spread once more. The oceans, stirred by currents and enriched by minerals from both the land and the skies, became a canvas of possibility. Into this restless environment, microbes began to multiply. They had survived the frozen silence of the Snowball Earth in tiny refuges, clinging to cracks in the ice or huddled near volcanic warmth, waiting for conditions to shift. Now, with the seas open and the chemistry alive with nutrients, they spread with astonishing speed. The waters teemed with microscopic activity. Bacteria of many forms thrived, breaking down minerals, exchanging gases, and weaving themselves into the cycles of the planet. Among them were the cyanobacteria, tiny architects of change, whose ability to capture sunlight and release oxygen made them critical to the transformation of Earth. These organisms were not newcomers. They had been present for billions of years, shaping the atmosphere in earlier ages. But after the long imprisonment of the world in ice, their return was like the turning of a key in a locked door. They began to release oxygen once again, filling the shallow seas with bubbles invisible to the eye but monumental in consequence. The spread of cyanobacteria created new patches of color in the seas. On the surface, they bloomed in great numbers, staining the waters green as they absorbed sunlight. Along the coasts, they grew in layered mats, their filaments binding sediments together. These mats created subtle ridges and textures that captured particles carried by the tides, building slim layers that thickened with time. Each layer recorded the daily rhythms of growth, the pulse of sunlight, and the rise and fall of tides. This was the quiet rebuilding of ecosystems. Microbial communities expanded in every direction, forming the base of a food web that had not yet grown tall. There were no fish to hunt these microbes, no animals to graze on the mats they created. The ocean was still a world of single-celled pioneers, yet within their smallness lay the seeds of what would come. The energy they captured from the sunlight and the oxygen they released into the water began to create conditions that larger and more complex organisms could one day use. The mixing of nutrients helped to accelerate this process. Phosphorus, iron, and other minerals washed from the land and rained from volcanic skies into the seas. Each tidal surge carried them into circulation, feeding the cyanobacteria and their microbial companions. Population booms followed, sometimes overwhelming the waters with dense blooms that changed the chemistry of their environment. When these blooms collapsed, their remains sank, providing food for other bacteria that decomposed them, releasing more nutrients into the cycle. These cycles of growth and decay were unstable, yet they drove the gradual enrichment of the oceans. Oxygen levels rose unevenly, higher near the surface and lower in the depths, but each wave of microbial productivity tipped the balance further toward a world that could sustain larger life. The microbes, though tiny, were reshaping the planet one breath at a time. Scientists studying rocks from this age can still find traces of these changes. Chemical signatures in ancient sediments reveal surges of oxygen, fluctuations in carbon, and shifts in sulfur that mark the activity of microbial communities. The faint textures of microbial mats are preserved in sandstone beds, their ripples frozen in time. These clues show us how the smallest organisms carried the weight of recovery, reforming the foundations of ecosystems after the planet's greatest freeze. It is remarkable to think that after tens of millions of years locked in silence, the first steps toward recovery were almost invisible. No forests sprang up, no creatures walked the land. Instead, the renewal began with specks of life too small to see, multiplying in waters stained red by iron and green by algae, beneath skies dimmed with storms and ash. These microbes, fragile yet relentless, created the oxygen that would allow larger forms to evolve, and in doing so, they rewrote the story of the Earth once again. As microbial mats spread along coasts and blooms thickened across the seas, the stage was set for something stranger. Soon, the oceans would give rise to beings that looked nothing like the microbes that had prepared the way. As the seas filled with microbial life and oxygen slowly rose, the oceans began to experiment with shapes that had never been seen before. From a world of single cells and mats of bacteria emerged something larger, something that could be seen without a microscope. On the sandy seafloor, strange oval forms began to appear, pressed flat against the sediment, their bodies ribbed and divided into quilt-like patterns. These were Dickinsonia, the first alien giants of the Ediacaran world. They were not giants in the sense of the animals that would come later. The largest Dickinsonia grew just over a meter long, but in a world where most life was still invisible to the naked eye, they must have seemed enormous. Their bodies lay flat, shaped like elongated ovals with ridges running across them from side to side. These ridges gave them the appearance of a segmented cushion, or a quilt sewn from repeating patterns. Their form was simple yet strange, with no head, no mouth, and no obvious organs. To us, they do not fit neatly into any category. They were neither plants nor animals as we know them today. They did not have bones or shells, nor did they possess leaves or stems. Instead, Dickinsonia represented an entirely different experiment, one that thrived for millions of years before vanishing almost without a trace. Some scientists believe they may have been early animals, related in some distant way to creatures that came later. Others argue they were something completely unique, a branch of life that had no successors. What we do know about Dickinsonia comes not from their bodies, which were soft and left no skeletons behind, but from the imprints they pressed into the ancient sands. When they died or were buried by shifting sediments, their outlines remained in the stone. These impressions, preserved for more than 500 million years, are the shadows of their presence. The sandstone layers of places like Australia, Russia, and Ukraine still carry these ghostly shapes, etched as if the creatures had just lain there yesterday. Some Dickinsonia fossils show faint traces of organic molecules within them. These chemical fingerprints reveal that they contained cholesterol, a type of fat molecule found in animals. This discovery hints that they may indeed belong somewhere on the animal tree of life, though their form remains unlike anything alive today. Their bodies seem to have grown by adding new segments at one end, expanding their quilt-like pattern as they aged. Unlike plants, they did not root themselves to the ground, and unlike true animals, they showed little sign of mobility. Yet Dickinsonia were not entirely still. Some fossil beds preserve overlapping impressions, suggesting that the creatures shifted slightly across the seafloor. They may have absorbed nutrients from microbial mats beneath them, leaving behind faint trails as they fed. This method of feeding was unlike grazing or hunting. It was more like lying on a banquet and absorbing it through the body. Their very shape seemed adapted to maximize surface area, making them efficient at drawing in whatever the sediments offered. Imagine standing above a shallow sea of that time. The floor beneath the water would be dotted with these quilted ovals, some as small as coins, others stretching longer than a human arm. They lay pressed flat against the sand, their ridges catching the dim light that filtered through the green-tinted waters. From above, they might have looked like alien leaves, or perhaps like the shadows of cushions resting on the seafloor. Silent, still, and yet alive, they were among the first visible organisms to change the character of the oceans. Their presence marked a turning point. For the first time, life had grown large enough to be seen from a distance. Dickinsonia transformed the seafloor from a flat microbial carpet into a landscape of bodies. They were not predators, they were not armored, they were simply experiments in becoming bigger, wider, and more complex. And in their quiet way, they laid the groundwork for life to expand in directions no one could have predicted. The impressions of Dickinsonia remain some of the most iconic fossils from the Ediacaran period. Each one is like a photograph taken in stone, capturing not only the creature itself, but the mystery of its nature. Was it an ancestor of animals, or the last of a forgotten lineage? Was it a success, or a beautiful dead end? The answers remain uncertain, yet the questions draw us closer to understanding how life first stepped beyond invisibility. And as Dickinsonia spread across the sandy seafloors, They were joined by other beings just as strange, rising into shapes that reached upward rather than lying flat. While Dickinsonia lay pressed against the seafloor, spread like patterned quilts in the sand, other beings were taking shape in the waters around them. Rising from the dim seabeds, tall forms appeared that looked like no animal we would recognize. They were called Charnia, named after the forest of impressions first discovered in the rocks of Charnwood Forest in England. Unlike the flat ovals of Dickinsonia, these creatures reached upward, their bodies stretching into frond-like shapes that swayed gently with the currents. Charnia grew in the shadows of deeper waters, in places where sunlight was faint or entirely absent. They did not rely on photosynthesis as plants do, for they were not plants at all. Instead, they absorbed nutrients directly from the water around them, their bodies acting like living sponges that captured what the currents carried. This ability allowed them to flourish in the darker reaches of the oceans, where microbial mats and surface blooms could not reach. Their bodies were long and slender, sometimes stretching more than a meter in height, with branching patterns that repeated in smaller and smaller scales. Each frond was divided into fine segments, giving them the appearance of a delicate feather or a giant leaf drifting in water. They anchored themselves to the seafloor with a simple holdfast, a structure that clung to the sediment or rock and kept them in place as currents swept past. From this anchor point, the fronds rose silently into the gloom, creating groves that resembled alien forests. To imagine them is to picture a world both haunting and beautiful. The seafloor, once bare, now held clusters of these leaf-shaped bodies, some standing alone, others forming dense gatherings. Their branches caught the flow of water, creating gentle eddies and shadows that provided tiny spaces where other microorganisms might gather. Though they had no eyes, no mouths, and no nervous systems, their presence transformed the environment. The seabed was no longer only a flat surface, dotted with microbial mats and quilted ovals. It had grown into a three-dimensional world, with vertical structures that gave it depth and texture. Charnia grew slowly, their lives measured not in days or seasons, but in spans of years. Their growth was silent and steady, shaped only by the nutrients drifting in the currents. They did not move, hunt, or flee, yet their stillness was a form of endurance. By holding their place in the dim waters, they could grow to sizes unimaginable for most organisms of their time. Their height gave them reach into currents that flowed above the seafloor, bringing them more nutrients than smaller creatures could capture. The fossil record preserves their outlines in fine detail. In slabs of sandstone, their frond-like bodies are etched as faint impressions, their branching patterns frozen in place. Each fossil is delicate, capturing the shape of a being that vanished long ago, yet still whispers its form to us through stone. These impressions reveal entire communities of Charnia, patches of seafloor where the fronds grew together like groves of strange, silent trees. What makes Charnia so fascinating is how alien they seem. They do not belong to any group alive today. They are not plants, for they lacked chlorophyll and could not use sunlight. They are not animals in the sense we know, for they had no stomachs or muscles. They represent a separate experiment in life's possibilities, one that lasted for millions of years before fading away. Their existence shows how many different ways life has tried to take shape, how many paths have been explored before narrowing into the branches that survived. Picture a diver descending into those ancient seas. At first, only darkness and haze would surround them. Then, shapes would begin to appear in the gloom, tall fronds swaying as though a breeze passed through them, their outlines faint against the water. An entire forest might stretch across the seafloor, a quiet world where nothing chased or fled, where growth was the only form of activity. It would feel both eerie and tranquil, like walking among shadows that have taken root. Charnia stands as a reminder that life's story is not only about movement, teeth, or speed. Sometimes it is about stillness, patience, and the slow capture of opportunity. These ghostly fronds transformed the seabed into something larger than a microbial plane. They reached into the vertical space of the ocean, turning flat landscapes into layered ones. In doing so, they created the template for future ecosystems, where height, reach, and structure would one day define forests, reefs, and kelp beds. And as Charnia spread across the dim seabeds, they were joined by other branching forms, fractal patterns that multiplied into vast gardens of strangeness, each one weaving the next step in life's unfolding story. As the ghostly fronds of Charnia swayed in the dim currents, other forms began to spread across the seabed, multiplying into shapes even more intricate. These were the Rangomorphs, organisms unlike anything alive today, whose very bodies were patterned with repeating fractals. Where Charnia stood as tall singular fronds, Rangomorphs sprawled into clusters, covering the ocean floor with branching, feathery bodies that seemed to mimic the geometry of mathematics itself. Their bodies followed a rule of endless repetition. Each branch split into smaller branches, and those split again into even finer divisions, repeating the same basic shape at different scales. This fractal design gave them an enormous surface area compared to their size, allowing them to absorb nutrients directly from the surrounding water. They had no mouths, no stomachs, and no muscles. Instead, their bodies acted like nets, catching dissolved substances from the currents. The greater the branching, the more efficiently they could feed. Imagine a garden of Rangomorphs spread across the seafloor. At first glance, it might look like a forest of ferns or corals, but upon closer inspection, every shape was built from repeating patterns, each smaller branch echoing the form of the whole. Some grew tall and plume-like, while others spread low, covering wide patches of sediment. Together, they formed meadows that stretched into the distance, swaying gently with every current. The seas of this time were dimly lit and often colored by minerals, so these gardens must have appeared shadowy and mysterious. Where sunlight did not reach, Rangomorphs flourished, unbothered by the absence of light. Their survival depended not on photosynthesis, but on the endless exchange of chemicals flowing in the water. This gave them an advantage in deep or murky environments where few other organisms could thrive. Fossil beds from Canada, Newfoundland, and parts of Europe preserve entire communities of these organisms. Their impressions in sandstone reveal vast patches where hundreds of Rangomorphs grew side by side, creating alien landscapes frozen in stone. Some grew as tall as a human, others remained small, like delicate ferns only a few centimeters long, but all shared the same basic fractal architecture, a design repeated at different scales across their bodies. To walk among them in those ancient seas would have felt like entering a dream of geometry. Every shape echoed itself, repeating in smaller and smaller details until the pattern seemed infinite. The seabed would have looked alive, with forms both orderly and otherworldly, as if nature had borrowed from mathematics to craft its earliest large experiments. The fractal design was more than beauty. It was an elegant solution to survival in an ocean rich in nutrients but unstable in its chemistry. By maximizing surface area, Rangomorphs could extract as much as possible from the water. They lived in a world without predators, so they could spread freely across the sediment, creating dense fields where space was the only limit. Their soft, delicate bodies needed no armor or defense. They simply grew, absorbed, and multiplied. Some Rangomorphs anchored to the seafloor with holdfasts, while others may have draped loosely across the sediments, their branches lying flat like lace against the sand. When buried by storms or shifting sands, their shapes were pressed into the seabed, leaving behind fossils that still display their fractal patterns in remarkable detail. These fossils are so well preserved that scientists can trace the repeating branches all the way from the largest structures down to the tiniest subdivisions. Their existence raises questions about what it means to be an organism. Were they animals, distant ancestors of later life, or were they part of a completely separate experiment, one that left no descendants? Their lack of obvious organs makes classification difficult. They were neither plants nor fungi, and their bodies show no clear relation to any living group. They were, in many ways, beings of their own category, existing for tens of millions of years before vanishing from the fossil record. Rangomorphs remind us that early life was not bound by the forms we know today. It was creative, experimental, and often alien in design. The fractal gardens that once spread across the ocean floor show how strange and beautiful life could be when it was free from competition, predation, and the rules that later ecosystems would impose. And as these fractal fields expanded, covering seabeds with intricate patterns, the oceans were beginning to stir with signs of change. For the first time, subtle marks appeared on the seafloor, trails that hinted at movement, as though some creatures were beginning to crawl across the mats and gardens, testing the boundaries of stillness. For millions of years after the ice retreated and the seas filled with alien gardens of strange, fractal-bodied organisms, the ocean floor remained a quiet and still place. Rangomorphs, frond-like forms, and quilted giants like Dickinsonia spread themselves across the sediment, but none of them seemed to move in any purposeful way. Life during this time was anchored, rooted, or simply drifting in the currents. The seafloor was a gallery of static shapes, a canvas where biology painted without motion. Yet in scattered places, scientists have discovered faint traces that tell of something new stirring. Impressions preserved in ancient microbial mats reveal delicate grooves, thin winding lines pressed into the sediment, as if some small creature had dragged itself across the seabed. These are among the earliest trackways in the fossil record, ghostly trails left not by the environment, but by life itself, testing the possibility of movement. The mats that captured these traces were themselves alive, carpets of bacteria and microbes that coated the ocean floor. They provided a soft layer that could be pressed into by anything that shifted across them. When conditions were just right, when sediment buried these mats before currents erased the marks, the trails were preserved for hundreds of millions of years. Today, when we uncover them, they appear as winding grooves and ripples, as though the seabed had been lightly brushed by a fingertip. The organisms that left these traces remain mysterious. They were not yet worms in the modern sense, nor animals with legs or fins. Most likely, they were soft-bodied beings, perhaps tubular or slug-like in form, capable of pushing their bodies against the sediment to inch forward. Some may have used muscular contractions to ripple across the surface, while others could have glided slowly by secreting mucus that helped them slip over the mats. Whatever their shapes, these were among the first creatures to leave behind evidence of purposeful movement, marking the beginning of mobility in the fossil record. The importance of these first movers was profound. For the first time, life was no longer bound to one spot. To move, even slowly, meant freedom to explore, to find new patches of nutrients, or to escape unfavorable conditions. It meant that the seafloor was no longer just a static garden of anchored forms, but a place where interactions could begin, where one organism could encounter another not by chance, but by seeking. The faint grooves in microbial mats whisper of curiosity, of exploration, of the earliest stirrings of behavior. Imagine the seabed during this time. Vast fields of fractal Rangomorphs and quilted Dickinsonia stretched across the sediment, their bodies swaying gently in the currents. Above them, the water was often cloudy with minerals and microorganisms, tinged with hues of green and red. And cutting across this still tableau, a faint trail would appear, winding between the anchored shapes, evidence that something alive had stirred, moved, and left its passing recorded in the microbial carpet. To see such a trail today is to glimpse not just the body of an ancient creature, but the very act of movement itself, frozen in stone. Some of these trackways suggest that organisms were not merely moving randomly, but following patterns. A few appear to lead toward nutrient-rich mats, as if the movers were seeking out food. Others suggest that these beings could change direction, adjusting their path. Such behavior hints at the beginnings of sensory ability, perhaps the capacity to detect chemical signals in the water or on the surface of the mats. These simple movements carried within them the seeds of complexity, the first steps toward the active, mobile animals that would later dominate the oceans. The arrival of movement began to change the balance of these ecosystems. Once, the seafloor had been layered by microbial mats that lay undisturbed for long stretches of time. But as organisms began to move across them, these mats were grazed upon, disrupted, and broken apart. For the first time, life was reshaping the environment in subtle, physical ways. Trails pressed into the sediment were not just records of journeys. They were evidence that ecosystems were beginning to feel the touch of living activity. Fossil beds from places like Newfoundland, Australia, and Russia preserve some of these earliest traces. They are not dramatic fossils of bodies, but quiet marks that would be easy to overlook if not for their significance. Each groove and winding path is a story of movement, a frozen record of life taking its first steps into mobility. In their quietness, they carry a power equal to any skeleton or shell because they speak of behavior, and behavior is the essence of living action. These first movers were still small, fragile, and soft, yet the simple act of crawling across the seabed was a revolution. It marked a threshold where life began to leave static existence behind, opening a future of interaction, pursuit, and change. From these faint trails would eventually grow the bustling, mobile ecosystems of the Cambrian Explosion, where predators, prey, and complex behaviors would unfold. But for now, in these earliest moments, the ocean floor was just beginning to stir with motion, as if life itself was waking up and learning to wander. And with these stirrings, the once still seafloor transformed into something more than a garden of anchored shapes. It became a landscape alive with possibilities, ready for the emergence of entire communities that would build upon the quiet paths laid down by the first movers. Beneath the shifting waters of the late Ediacaran seas, life gathered into something new, something larger than single creatures moving quietly across microbial mats. For the first time in Earth's history, entire communities began to form on the seafloor. These were not bustling cities of predators and prey as would come later, but delicate assemblies of soft-bodied organisms spread like a living tapestry across the sediment. It was a world without teeth, without claws, without the sharp edges of conflict. In many ways, it was the closest life has ever come to a true Garden of Eden. The seafloor was carpeted with microbial mats, sticky layers of bacteria that both fed and anchored larger organisms. Into this soft foundation grew the strange and unearthly creatures of the Ediacaran biota. Dickinsonia spread out like ribbed ovals, their quilt-like forms pressed against the mats, absorbing nutrients directly through their bodies. Beside them rose the ghostly fronds of Charnia, their leaf-like bodies stretching into the currents, drawing sustenance from the water around them. In clusters, fractal Rangomorphs branched into delicate patterns, filling the seabed with shapes that resembled gardens of lace. Together, they created a landscape unlike any ocean we know today. Imagine a field of immobile fronds, rising gently from the seabed, their surfaces swaying in the slow push of ancient tides. Between them lay oval quilts spread flat upon the mats, their ribbed outlines catching the dim light that filtered from above. No fish darted among them, no crabs scuttled across the sand, no starfish clung to the rocks. Instead, the seafloor was still, its life forms anchored in place, absorbing energy from water and sediment in silence. What made this ecosystem so extraordinary was its peacefulness. For the moment, there were no predators. The creatures of this age had no shells to protect them, no armor to hide behind, and no means of attack. They grew large and soft because they could. The absence of danger allowed them to sprawl across the seabed, reaching sizes that would have been impossible in a later world filled with hungry mouths. A Dickinsonia could stretch more than a meter across, lying undisturbed for years, feeding quietly from the mats beneath it. Charnia could tower in groves, rising as tall as small trees, never cut down by grazers. The ecosystem functioned more like a shared garden than a competitive battlefield. Nutrients flowed into the seas after the great floods, feeding microbial mats, which in turn supported the soft-bodied giants resting above them. The balance was delicate, yet it was stable enough to allow whole communities to form. Clusters of organisms grew together in gentle harmony, their shapes overlapping and intertwining. In some places, fossil beds preserve these ancient neighborhoods exactly as they fell, capturing the outlines of dozens of organisms side by side, as though a snapshot of the seafloor had been pressed into stone. There were, of course, subtle interactions. Some creatures may have competed for space on the mats, others may have shaded one another with their fronds, changing the flow of nutrients. And as the first movers stirred across the seabed, they may have disrupted the microbial carpet, leaving trails through the still communities. Yet even these interactions carried none of the violence that would define ecosystems in the Cambrian. Here, in this moment, life grew without fear. The Ediacaran seafloor was also a place of experimentation. The forms that flourished here were diverse and strange, with no clear connection to the animals we know today. Some absorbed nutrients directly through their surfaces, others may have filtered water slowly, pulling in what they needed. Their bodies were soft, ephemeral, and in many ways alien, as though evolution was sketching possibilities without yet settling on a permanent design. For nearly 30 million years, these experiments dominated the oceans, spreading across continents and filling shallow seas with their quilted, branching, and fronded forms. When we look back at this time, it is striking to think of how quiet it must have been. No sudden lunges of predators, no frantic escapes of prey. Just a slow, patient unfolding of life in forms that drifted gently with the water or lay pressed against the mats. The seas themselves were unstable, their chemistry shifting, their oxygen levels fluctuating. Yet within those waters, these soft-bodied creatures carved out a stage of peace that would never come again. This Garden of Eden could not last forever, but for a brief span in Earth's history, life was allowed to grow in size, in variety, and in strangeness, without fear of being consumed. It was a fragile balance, but it set the foundation for what would come next, when survival would require new strategies and the stillness of the seafloor would give way to a world of movement and conflict. In this quiet chapter of Earth's story, the oceans belonged to creatures that lived without fear. The seafloor, already transformed into a strange quilt of soft-bodied organisms, was shaped by an absence rather than a presence. There were no claws slicing through the water, no teeth tearing at flesh, no shells clattering as defenses. It was a time before nature had learned to arm itself. In this stillness, life was free to sprawl, to spread, and to experiment with forms that seemed impossible in the worlds to come. The beings of this age grew large not because they fought their way to survival, but because nothing existed to stop them. Dickinsonia could stretch across the microbial mats, absorbing nutrients through its quilt-like body without ever being disturbed. Rangomorphs branched in endless fractal patterns, their delicate forms covering wide patches of seabed without fear of being torn apart. Charnia and its kin rose like ghostly fronds in silent groves, reaching upward into the dim waters, never cut down by grazers. The very stillness of the ecosystem allowed size and strangeness to flourish. Without predators to force change, life grew at its own unhurried pace. Growth was slow, patient, and quiet. An organism could take years, perhaps decades, to reach its full size, and nothing would disturb it once it did. Communities spread not by movement or conflict, but by simple reproduction and expansion. One frond could branch into many. One quilt could divide and form new patches. Over vast stretches of time, they carpeted the seafloor, turning it into a landscape of patterns and textures, more like a woven tapestry than the chaotic scenes of later oceans. The rhythms of this world were gentle, shaped by tides and currents rather than by the chase of predator and prey. The rise and fall of the moon's pull carried nutrients into shallow waters, feeding microbial mats and sustaining the giants that rested upon them. Storms might stir the waters or blanket the seafloor in sediment, yet once the chaos passed, life continued undisturbed. There was no need for rapid recovery from attack, no arms races of adaptation. The creatures of this world lived within the pace of geology itself, bound only by the chemistry of their seas and the oxygen available in their waters. The absence of predation created a kind of freedom. Forms could stretch into extraordinary shapes, experimenting with fractals, spirals, and quilted designs that defy comparison to modern animals. Energy could be devoted not to armor or speed, but to sheer growth. The fossil record captures these forms as faint impressions in sandstone, outlines of bodies that once rested gently on microbial carpets. Some were discs, others fronds, others ovals with ribbed patterns. Each shape hints at the creativity of evolution in a world where survival required no weapons. It is strange to imagine an ocean without fear, but the evidence suggests that this was exactly what existed. Fossil beds preserve entire communities lying side by side with no sign of attack or destruction. Bodies appear intact, their edges undisturbed, as if they lived and died without violence. This peace allowed ecosystems to persist for millions of years in delicate balance, their growth steady and their diversity increasing slowly. Yet, this stillness was not eternal. The very lack of predators may have set the stage for change, for once the first signs of mobility and feeding appeared, the balance would shift forever. But in this moment, in this world, before claws, shells, and teeth, life knew only quiet expansion. The seafloor was filled with patterns of growth, with organisms spreading across vast areas, their shapes left undisturbed for ages. From this silence, the foundations were being laid for everything to come. The experiments of the Ediacaran biota, unshaped by the pressure of predation, created a variety of forms that would later vanish, but their presence transformed the oceans into something new. A living fabric stretched across the seabed, peaceful and strange, a glimpse of what life can be when it is free to grow without fear. And just beyond this fragile harmony, change was beginning to stir, subtle at first, but destined to unravel the stillness that had defined this age. As the peaceful seas of the Ediacaran world stretched on, the seafloor became a gallery of forms that seem almost too strange to belong to Earth. Unlike the fronds of Charnia or the quilted bodies of Dickinsonia, some organisms left behind shapes that confound even the most experienced paleontologists. Their bodies pressed into the sediment in patterns that defy neat categories, leaving behind discs, spirals, and quilted carpets unlike anything alive today. When scientists first uncovered these fossils, they struggled to find words for them. Some resembled coins, round and flat, imprinted into sandstone as if stamped onto the seabed. Others curled into spirals, twisting gently as though frozen mid-turn. Still others spread like great rugs across the sediment, their surfaces divided into geometric ridges and blocks, as though stitched together in patterns. These shapes were not plants, not animals, not fungi, and not microbes, at least not in any way we understand them. They belong to an entirely different chapter of biology, a cast of characters with no modern relatives. One of the most mysterious of these is the fossil known as Tribrachidium. Preserved as a circular imprint with threefold symmetry, it looks almost mechanical, like a design pressed by a careful hand rather than grown by a living body. Its spiral grooves may have directed water toward its center, suggesting it filtered nutrients as they flowed by. But no modern organism grows with this pattern, and its place on the tree of life remains uncertain. Other fossils, like Cyclomedusa, appear as simple discs, yet their surfaces often carry faint radiating lines, as though they were the bases of soft-bodied organisms that anchored into the sediment. Some paleontologists once mistook them for jellyfish impressions, but their stillness, their consistency, and their association with microbial mats suggest they were something altogether different. Instead of floating freely in the water, they may have been immobile forms, pressed flat against the seabed, absorbing nutrients from the microbial carpets below. Even more confounding are the quilted organisms such as Paleopiscnus, which stretched across the sediment in chains of repeating segments. They look like strings of beads pressed into stone, each chamber linking to the next. Were they colonies of many individuals, or the body of a single creature divided into compartments? The answer remains elusive. Fossil after fossil reveals their repeating pattern, yet their biology is unlike anything seen in animals or plants. These shapes raise questions about what it truly means to be alive. Modern ecosystems are divided into categories we understand: animals that move and feed, plants that grow and photosynthesize, fungi that decompose. But in the Ediacaran world, the rules were not yet written. Evolution experimented with forms that do not fit our definitions, bodies that were neither rigid nor easily divided into organs. Many absorbed nutrients directly through their surfaces without mouths or stomachs. Some grew by simply adding more fractal branches or quilted segments, expanding outward without limit. Their bodies were patterns of repetition, geometry brought to life. For scientists, the challenge lies in classification. Where do these creatures belong? Do they represent an early branch of animals that later died out, leaving no descendants? Or were they something entirely separate, an experiment in multicellularity that ended before the Cambrian Explosion? The fossils provide impressions but not answers, shadows pressed into stone that suggest life but conceal its true nature. The mystery deepens because these shapes show no sign of defense or aggression. No shells, no teeth, no weapons, no wounds. They lived in a time before predation, when survival required only to absorb and to grow. Perhaps this freedom allowed their bizarre designs to flourish, unchecked by the pressures that would later force life into sharper, more defensive forms. Their beauty lies in their strangeness, in the fact that they seem to come from a different set of evolutionary rules, a lost world of geometry and soft tissue that left only faint imprints behind. When we look at these fossils today, preserved in rocks across Australia, Namibia, Russia, and Canada, they remind us that Earth's story is not just about the ancestors of creatures we know. It is also about entire experiments that vanished, leaving behind puzzles pressed into stone, discs, spirals, and quilts that resist every attempt to explain them fully. They are shapes that whisper of life, yet defy understanding, a reminder that evolution is not a straight line, but a branching, tangled history filled with possibilities we may never fully comprehend. And as these strange beings spread across the seafloor, filling it with patterns unlike anything before or since, the chemistry of the seas was quietly shifting once again, preparing the stage for larger bodies and new forms of life that would soon change the balance forever. As the seas of the Ediacaran age filled with soft-bodied forms, the hidden chemistry of the planet was quietly shifting. The great floods that followed the melting of Snowball Earth had stirred the oceans, unlocking minerals from the continents and mixing nutrients through the shallows. These ingredients fueled blooms of microbes, especially cyanobacteria, which exhaled oxygen into the waters and into the skies above. For the first time in hundreds of millions of years, oxygen levels began to climb toward thresholds that could sustain larger, more complex bodies. Before this, the atmosphere and oceans were often starved of oxygen, a world where small, simple organisms dominated because they required so little. In such a thin environment, bodies could not grow large, nor could they sustain the energy needed for movement or for complex tissues. But as oxygen began to rise, possibilities expanded. The invisible gas, making up a growing fraction of the air and dissolving into the seas, allowed life to stretch, to grow, and to become stranger than before. This rise did not happen in a straight line. Oxygen surged and retreated, climbing in great bursts, then faltering again as oceans consumed it through chemical reactions, or as blooms of microbes collapsed and rotted away. These fluctuations kept life fragile. An organism might thrive in one place where oxygen levels were high, only to falter when currents shifted or when waters grew stagnant. In some areas, shallow seas became havens of growth, while deeper basins remained suffocating and dark, trapping life close to the coasts. Even with these limitations, the climb of oxygen was enough to open new doors. Dickinsonia, with its quilted form, could grow to sizes measured in feet, far larger than anything seen before. Rangomorphs expanded into vast fractal colonies, branching again and again, their bodies supported by the energy that higher oxygen levels made possible. Frond-like organisms, such as Charnia, reached upward into the currents, their tall, leaf-shaped bodies swaying in waters that carried both nutrients and the precious gas that sustained them. Oxygen allowed tissues to exchange energy more efficiently, letting bodies expand beyond the thin, delicate films of earlier microbes. The presence of oxygen also gave the seas a new character. In some places, its interaction with dissolved iron created chemical patterns that left traces still visible in rocks today. In others, the gas accumulated near the surface, creating layers of water that differed from the depths below. These gradients shaped where life could thrive, drawing communities into certain regions and leaving other areas barren. The seafloor became a patchwork of habitability, places of abundance lying beside places of silence. Scientists studying this period can see the fingerprints of these changes in the chemistry of ancient sediments. Ratios of carbon, sulfur, and iron tell the story of oxygen's uneven rise, marking times when the gas spread through the oceans and times when it crashed back to near zero in parts of the world. These records show how delicate the balance was, how close life always stood to the edge of collapse. Yet each surge, however brief, gave organisms a chance to grow larger, to test new forms, and to expand the possibilities of evolution. For the creatures of the Ediacaran world, this meant a strange mix of fragility and opportunity. They could become giants compared to what came before, but they remained at the mercy of their environment. If oxygen faltered, entire communities could vanish, preserved only as faint imprints in the sandstone beds that recorded their shapes. If oxygen held steady, even for a short span, life flourished into forms that seemed more alien than earthly. The rise of oxygen to critical levels was not just a chemical event. It was the invisible scaffolding that allowed the first great experiments of multicellular life to unfold. It provided the breath behind their soft bodies, the unseen force that lifted them into size and complexity. Without it, the discs, fronds, and quilts of the Ediacaran seafloor could never have grown as they did. And yet, as these organisms thrived in their fragile Eden, the instability of oxygen levels meant that their future was uncertain. Their world was built on a foundation that could shift without warning, a reminder that even abundance can carry with it the seeds of loss. As oxygen pulsed through the seas, setting the stage for growth and for collapse, life continued its patient unfolding. From this fragile balance, the next transformations would rise, each one carrying the imprint of oxygen's invisible hand. The oceans of the Ediacaran age were alive with possibilities, yet they were also fragile in ways that are difficult to imagine today. Life was tied closely to the chemistry of the seas, and even the smallest shift could ripple outward across entire ecosystems. The rising oxygen levels had opened new doors for growth, but they were never stable. Instead, the ocean swung between abundance and scarcity, offering bursts of opportunity followed by sudden collapse. This constant flux became the rhythm of existence, shaping everything that lived upon the ancient seafloor. Nutrients poured into the seas after the great floods that followed the melting of global ice. Minerals washed from the raw, barren continents and spilled into shallow waters, feeding microbial blooms that tinted the seas in strange hues. These blooms provided the foundation for larger organisms, sustaining communities of Dickinsonia, Charnia, and Rangomorphs that sprawled across the seabed. But the balance was precarious. When nutrients were abundant, these communities expanded rapidly. When the nutrients were depleted, they withered just as quickly. These cycles left ecosystems vulnerable, unlike modern animals that can move or migrate when resources grow scarce. Most Ediacaran organisms were fixed in place. A Dickinsonia could not swim to a richer patch of seafloor. A Charnia grove could not relocate to fresher currents. They depended entirely on the conditions around them. If nutrient levels dropped or oxygen faltered, they had no defense but to endure, and often they could not. Entire communities might collapse in silence, leaving behind only their impressions pressed faintly into the mats beneath them. Even small changes in the oceans carried outsized effects. A shift in temperature could alter circulation patterns, changing how nutrients were distributed. A surge of volcanic ash could enrich the seas for a time, only to choke them later when blooms crashed and decomposed. Oxygen might accumulate for a brief window, fueling larger growth, then decline again as chemical reactions in the oceans consumed it. Life was tied to these swings, unable to control them, and forced to adapt within narrow margins. The fossil record gives glimpses of this instability. In some layers of sandstone, entire clusters of organisms appear together, as though flourishing in a moment of abundance. In the very next layers, they vanish, replaced by empty beds of microbial mats, suggesting a sudden downturn. These alternating records of presence and absence capture the pulse of the seas, the boom and bust of ecosystems caught in fragile balance. This fragility also shaped the forms that life took. Many organisms grew by absorbing nutrients directly from the water or the microbial mats beneath them. It was an efficient strategy when resources were plentiful, but it left them vulnerable when conditions turned lean. Without mouths, stomachs, or circulatory systems, they had little means to store energy or to survive prolonged shortages. Their lives were tuned to the immediate state of the ocean around them, thriving in surges of plenty and fading when the tides of chemistry shifted. For millions of years, this dance of rise and fall continued. Life expanded across the seafloor in waves, each generation building upon the chemical opportunities of its moment. Yet each expansion carried the risk of collapse, because the seas were not steady reservoirs, but restless systems, swayed by geology, climate, and the deep currents of the earth itself. The Ediacaran ecosystem was a lesson in impermanence, a world where flourishing and fading were inseparable, bound together like the tides. And while these organisms lacked predators, their greatest challenge came from the environment itself. It was the chemistry of the seas, the shifting balance of oxygen and nutrients that dictated their survival. In this way, the Ediacaran world was both generous and unforgiving, a place where life could grow large and strange, but only so long as the balance held. From this fragile equilibrium, new possibilities were slowly emerging. As organisms tested the limits of their environment, they prepared the stage for the transformations that would follow, when ecosystems would no longer be shaped only by chemistry, but also by the pressures of interaction, competition, and eventually, predation. While the fragile ecosystems of the Ediacaran seas rose and fell with the chemistry of the oceans, the very face of the planet itself was also in motion. Continents drifted slowly across the surface of the earth, carried on tectonic plates that shifted like rafts upon a restless sea of mantle rock. The supercontinent known as Rodinia, which had once gathered much of Earth's land into a single massive body, had already broken apart by this time. What followed was an age when the continents wandered in new directions, scattering into unfamiliar patterns that gave the world a geography unlike any we would recognize today. This drifting created landscapes that were profoundly alien. The outlines of the continents were not the ones we know now. South America, Africa, North America, and Asia as we think of them had not yet taken shape. Instead, the land masses were fragmented into strange clusters, their shorelines twisted and scattered. They lay in different latitudes, some crowded close to the equator, others drifting toward the poles. The oceans between them were vast, and the currents that flowed through those oceans shaped climates, ecosystems, and the distribution of life. To piece together this geography, scientists rely on the faintest of clues locked in ancient rocks. One of the most important tools is paleomagnetism, the record of Earth's magnetic field frozen into minerals as they cooled. When lava solidified or sediments were laid down, the iron particles within them aligned with the planet's magnetic field, pointing toward the north of that time. Millions of years later, when these rocks are studied, the orientation of those particles reveals where the land lay in latitude. By comparing rocks from across the world, scientists can reconstruct the drifting paths of continents long vanished into new forms. These reconstructions show that during the Ediacaran period, Earth's continents were scattered across both hemispheres. Laurentia, the ancient core of North America, rested near the equator. Gondwana, a massive landmass that contained what would one day become Africa, South America, Antarctica, Australia, and India, stretched across much of the southern hemisphere. Smaller blocks of crust drifted in between, fragments of Rodinia's breakup still seeking new positions on the globe. The arrangement gave Earth a geography far removed from today's familiar world map, a patchwork quilt of continents stitched across alien seas. The climate of this scattered Earth was deeply influenced by the positions of the continents. Shallow seas spread across flooded coastlines, creating broad shelves where Ediacaran life flourished. These continental margins were cradles for the soft-bodied creatures that spread across microbial mats, since shallow waters were rich in sunlight and nutrients. Deeper oceans, far from continental shelves, remained dark and inhospitable, their chemistry less stable, their oxygen levels too low to support much life. Thus, the drifting of continents determined where life could find footholds, guiding the spread of ecosystems across the globe. The movement of continents also meant constant change. Over millions of years, land masses drifted closer together or pulled farther apart. Mountains rose where plates collided, while rift valleys opened where they separated. These changes altered the flow of ocean currents, reshaped coastlines, and influenced global circulation. What might have been a thriving shallow sea in one era could vanish beneath the uplift of mountains or retreat into the depths as land drifted away. For life clinging to the margins, geography was destiny, setting the boundaries of where communities could grow and where they would disappear. The alien quality of this geography is difficult to overstate. Imagine looking at Earth from space during the Ediacaran period. The continents below would not form the shapes we know today. There would be no recognizable Africa with its bulging western edge, no familiar outline of Eurasia, no long stretch of the Americas. Instead, strange landmasses would sprawl across the globe, their coasts drowned beneath high seas, their forms unrecognizable. The oceans would dominate the view, with only fragmented patches of land interrupting the blue expanse. From the perspective of today, it would look like another planet altogether, a foreign world with a face we would struggle to identify as Earth. Yet this drifting world was not static. Its alien geography was part of a longer story, the endless rearrangement of continents that continues to this day. The same forces that scattered the remnants of Rodinia would later bring land together again into new supercontinents, only to break them apart once more. The restless shifting of the Earth's crust has been the backdrop to life's entire history, shaping where ecosystems rise and fall, guiding the currents that carry nutrients, and driving the climates that organisms must endure. As the continents of the Ediacaran world drifted in their unfamiliar patterns, they created the stage on which the soft-bodied organisms of the time lived and died. Their positions determined the shape of shallow seas, the reach of tides, and the flow of currents that carried oxygen into the waters. In this way, the alien geography of the time was not just a map of land and ocean, but a hidden architect of life's fragile balance. The alien geography of the Ediacaran world has long since vanished, its continents drifting into new forms and its coastlines erased by time. Yet the memory of that world has not been lost entirely. It lingers, preserved not in photographs or drawings, but in the language of the rocks themselves. Layer upon layer of stone carries within it chemical signatures, delicate tracers that reveal the state of ancient oceans, the breath of the atmosphere, and even the floods that once drowned the continents. To scientists, these rocks are not silent. They whisper the story of a planet in transition, a world reborn from ice and reshaped by chemistry. Among the most important of these whispers are the isotopes of carbon. Every atom of carbon has the same number of protons, but some carry extra neutrons, making them heavier. These heavier and lighter versions, known as isotopes, behave differently in chemical reactions. Life, in particular, tends to prefer the lighter carbon isotope, building it into organic matter. When blooms of life thrived in the oceans and later died, their remains buried in sediments, they altered the balance of isotopes left behind in the waters. The rocks that formed from those sediments locked these signals away. Millions of years later, when scientists measure the ratio of carbon isotopes in Ediacaran rocks, they find evidence of the booms and busts of ancient ecosystems, their quiet rise and sudden collapse written in chemical code. Sulfur, too, left its fingerprints. In the oceans of the Ediacaran, sulfur cycled through complex pathways, shaped by microbes that fed on it and by chemical reactions with oxygen. The isotopes of sulfur reveal how oxygen levels shifted in different parts of the seas. When oxygen was scarce, sulfur behaved one way, producing certain isotopic patterns. When oxygen surged, those patterns changed. In this way, sulfur isotopes serve as markers of the uneven rise of oxygen across the planet, showing when and where conditions were favorable for larger, more complex life. The stones that hold these signals are like diaries of the oceans, recording the fragile balance of chemistry that defined the age. Iron tells another part of the story. In waters poor in oxygen, iron dissolved and drifted freely, but when oxygen became abundant, it combined with iron to form rust-colored minerals. These settled to the seafloor, creating chemical layers that still gleam in ancient rocks. Some of the eerie red hues of sediments from this time mark intervals when oxygen briefly surged, enough to oxidize iron on a vast scale. Elsewhere, layers of darker stone capture moments when oxygen dwindled, leaving iron to linger dissolved in the seas. Together, these alternating signatures sketch a portrait of oceans that were anything but stable. By piecing together sulfur, carbon, and iron isotopes, scientists can reconstruct a picture of the Ediacaran world in remarkable detail. They can tell when life flourished in shallow seas, drawing down carbon and releasing oxygen. They can see when blooms collapsed, leaving oceans depleted. They can trace the fluctuations of oxygen as it rose toward critical thresholds, only to retreat again. Each shift is preserved in stone, a faint echo of tides and storms and chemical changes that shape the living world. What is most striking is how these chemical tracers align with the fossils of the time. In layers where isotopes suggest oxygen was plentiful, the imprints of larger organisms are more common. Dickinsonia, Charnia, and the fractal Rangomorphs are found in rocks that bear the marks of oxygen-rich waters. In layers where oxygen faltered, fossils vanish, replaced by the quiet textures of microbial mats. The chemistry and the biology are woven together, two halves of the same ancient record. In this way, the rocks themselves become storytellers. They do not show us the alien creatures directly, but they reveal the world those creatures lived in. They describe seas tinted red with oxidized iron, oceans surging with nutrients that sparked microbial booms, and atmospheres thick with greenhouse gases and volcanic ash. They hold the evidence of floods that spread across the continents and of chemical cycles that rose and collapsed like breath. The Ediacaran world may seem impossibly distant, yet when we hold a piece of sandstone marked with the faint outline of a Dickinsonia or measure the isotopes within a slab of limestone, we are holding the memory of that time. Locked inside these ancient stones are the rhythms of the earliest complex ecosystems, the record of Earth as it recovered from ice and prepared for the explosion of life that would follow. And as we listen more closely to the voices of these rocks, we begin to see not just the chemistry of oceans and skies, but the fragility of the creatures that depended on them, poised between survival and disappearance in a world that was still learning how to sustain complexity. The chemical tracers hidden in ancient rocks give us a broad picture of the Ediacaran world, but to glimpse the creatures themselves, we must turn to another kind of record. Unlike the sturdy shells and bones that would later define the fossil record of the Cambrian and beyond, the organisms of the Ediacaran age left behind only the faintest marks of their passing. They were soft-bodied, fragile, and ephemeral, their forms vanishing quickly after death unless preserved under extraordinary conditions. What remains today are not skeletons or hardened remains, but shadows pressed into stone, delicate impressions that whisper of beings long gone. The key to these shadows lies in the microbial mats that blanketed the seafloor. These mats, made up of countless layers of bacteria, were sticky and cohesive, holding together like living carpets. When an Ediacaran organism such as Dickinsonia or Charnia rested on them, its weight pressed into the soft surface. If sediment washed over that mat soon after, it buried the impression and sealed it away. Over time, the layers hardened into sandstone, capturing the outline of the creature in astonishing detail, down to the ribs of a quilted body or the branching symmetry of a frond. These fossils are not bodies, but the molds left behind when the body itself vanished. They are negative spaces, the imprint of where life once lay. That is why paleontologists often describe them as ghostly. The creatures themselves were soft as jelly, dissolving quickly after death, leaving only the faint signature of their contact with the sea floor. The preservation is so delicate that even slight disturbances could have erased them, but in certain places the conditions aligned perfectly to freeze their shapes in stone. One of the most famous examples comes from the sandstone beds of South Australia in the Ediacaran Hills, where the period takes its name. Here, slabs of rock carry the outlines of Dickinsonia in dozens of sizes, from small ovals to sprawling forms more than a meter across. Their ribbed, quilted structures appear almost as if they had been stamped into clay. Nearby, impressions of Charnia rise like frozen leaves, their leaf-like fronds etched into the rock with remarkable clarity. Other sites in Namibia, Russia, Canada, and Newfoundland hold similar treasures, each capturing a fragment of the lost seafloor communities. Yet for all their beauty, this fossil record is perilously fragile. Because it relies on impressions in sandstone, it tells us only part of the story. Many organisms may have lived in the Ediacaran seas that left no trace at all, dissolving before they could ever be captured. Others may have been erased by currents, storms, or the slow churn of sediments. What survives is likely a small and biased sample of the true diversity of the time. The fossil record here is like a faded photograph, a partial glimpse through a window clouded by time. Even so, the shadows are revealing. The outlines show us the size, the shape, and often the symmetry of these strange creatures. Some impressions even preserve fine details, like the branching patterns of fractal Rangomorphs or the faint ridges of quilted Dickinsonia. In rare cases, the way an organism shifted or decayed left layered imprints, showing how it may have grown or moved. These are not just fossils, they are frozen gestures, moments of interaction between living bodies and the seafloor captured across millions of years. The fragility of this record forces scientists to be cautious. Every slab of sandstone must be studied carefully, each faint outline mapped and compared, because there is so little margin for error. New discoveries can overturn assumptions, revealing forms that were once unknown or misunderstood. In some cases, what looked like a simple disk may turn out to be part of a larger, more complex body. In others, overlapping impressions may show that organisms grew in crowded communities rather than in isolation. Each detail adds depth to the picture, turning faint shadows into a richer story of life's early experiments. What makes these fossils especially haunting is their uniqueness. Unlike the bones of dinosaurs or the shells of trilobites, they cannot be held in the hand with weight and texture. They exist as flat imprints, almost like footprints left in wet sand, fragile evidence that can crumble if handled carelessly. They are whispers rather than voices, and yet they are all we have to connect us to beings that once covered the seafloor. From these faint outlines, we learn that the Ediacaran world was not empty, but full of forms that spread, grew, and flourished for millions of years. Their bodies were fragile, their record faint, yet through the patience of stone they endured, carrying their story forward into our time. And just beyond these ghostly impressions, another transformation was approaching, one that would challenge the stillness of this world and bring about the disappearance of many of these delicate forms. The sandstone beds that preserve the ghostly outlines of Dickinsonia, Charnia, and other Ediacaran forms are like windows into a vanished world. Yet what makes them even more haunting is that these creatures appear only in rocks of a very specific age. Beyond a certain boundary in time, their shapes no longer appear. The quilts, the fractals, the disks, and the fronds that once covered the seafloor simply vanish from the fossil record. This quiet absence is one of the great mysteries of Earth's history, for the Ediacaran biota did not fade slowly over hundreds of millions of years, but disappeared almost entirely just before the Cambrian Explosion. Scientists have long sought to understand why. One possibility is that the chemistry of the oceans turned against them. The rise of oxygen had enabled their growth, but it was never stable. Fluctuations in the balance of gases could have pushed them beyond their limits. If oxygen levels fell even slightly, the large, soft-bodied Ediacaran organisms would have struggled to survive. Their simple tissues, dependent on absorbing nutrients and gases directly through their surfaces, may not have been able to endure prolonged scarcity. The fossil record hints at these fluctuations, with isotopic signals suggesting sudden downturns in oxygen availability. A crash of this kind would have been catastrophic, reducing vast communities of fronds and quilts to silence. Another possibility lies in the arrival of competition. The boundary between the Ediacaran and Cambrian periods is one of the most dramatic transitions in the history of life. In the Cambrian, ecosystems filled with animals that had never existed before, creatures with mouths, guts, shells, and the ability to move with purpose. These early Cambrian animals could burrow into sediments, graze upon microbial mats, and actively seek food. For the first time, life could pursue life. Predation had arrived, and with it, the rules of survival were rewritten. For organisms like Dickinsonia or Rangomorphs, which absorbed nutrients passively and had no defenses, the emergence of grazers and predators may have been devastating. Burrowing animals could have torn up the microbial mats they depended upon. Grazers could have scraped them away, while predators could have targeted their soft bodies directly. In a world that had once been free of teeth, claws, and shells, the sudden appearance of these adaptations would have shifted the balance irreversibly. The peaceful Garden of Eden on the seafloor gave way to a world of interaction, competition, and conflict. There is also the question of adaptability. The Ediacaran organisms were remarkably successful in their own time, covering seafloors across the globe for tens of millions of years. Yet they may have been too specialized for their environment. Their unique body plans, so alien compared to modern animals, might not have been flexible enough to survive in ecosystems that were rapidly changing. Evolution, in this sense, can be merciless. What works brilliantly in one age may become a weakness in the next. The delicate geometries of Rangomorphs and the quilted symmetry of Dickinsonia may simply have been evolutionary experiments that ended when conditions shifted. The disappearance was not total. A few lineages may have survived into the Cambrian, their descendants hidden within the explosion of new forms. Traces of similarity between Ediacaran fossils and early Cambrian animals suggest that some genetic threads were carried forward, woven into the fabric of modern life. But the majority of the strange, soft-bodied organisms left no descendants. Their legacy lies only in the impressions etched into sandstone, silent reminders of an entire ecosystem that thrived and then was lost. The silence they left behind is striking. One moment the seafloor was filled with alien gardens of quilts and fronds, and the next it was transformed into a battlefield of shells, burrows, and predators. It is one of the clearest boundaries in the history of life, a moment when evolution shifted gears and set the stage for the animal-dominated world we know today. From their disappearance, questions echo. Was it an oxygen crash that suffocated them, or the rise of competition that overwhelmed them? Was it both, working together in a cascade of environmental and biological change? The rocks preserve only fragments of the story, leaving us to piece together their fate from chemical traces and fossil shadows. What is certain is that the Ediacaran biota lived in a fragile world, poised between abundance and collapse. Their silent disappearance marks not only the end of one of Earth's strangest ecosystems, but also the beginning of the age that would give rise to the ancestors of every animal alive today. The silent disappearance of the Ediacaran creatures left the seafloor strangely bare, yet beneath that stillness, something remarkable was brewing. The world had been reshaped by floods that followed the melting of global ice, and though many of the soft-bodied pioneers had vanished, the groundwork they laid did not fade with them. Their existence had altered the oceans, enriched the sediments, and shifted the balance of chemistry. In their wake, the seas were ready for a transformation unlike anything that had ever happened before. The legacy of the great floods was not only destruction, but also renewal. When glaciers melted and torrents of water scoured the continents, they carried with them vast amounts of minerals and nutrients. These elements poured into the oceans, feeding microbial blooms that surged across shallow seas. For millions of years, this process repeated, layering sediments with phosphorus, nitrogen, and trace metals. These ingredients became the raw materials for complexity. They created an environment where life could grow larger, build stronger tissues, and experiment with new ways of living. Oxygen, too, had risen to levels that changed the rules. The blooms of cyanobacteria and algae, combined with geological processes that buried carbon in sediments, allowed oxygen to accumulate in the atmosphere and dissolve into the oceans. Though still fluctuating, its average levels were far higher than during the frozen silence of Snowball Earth. For the first time, there was enough oxygen to support organisms with circulatory systems, muscles, and nerves. The soft-bodied quilts and fronds of the Ediacaran had taken advantage of this oxygen in their own limited way, but their disappearance left room for new forms to rise, ones that would use oxygen to power motion, speed, and predation. This shift was not immediate. The Cambrian Explosion, as it would come to be called, did not erupt suddenly in a single moment, but built upon foundations laid during the late Ediacaran. The microbial mats that once covered the seafloor had stabilized sediments, preparing them for burrowing creatures that would later plow through them. The strange geometries of Rangomorphs and the ribbed quilts of Dickinsonia had shown that large bodies were possible, even if their designs were ultimately fleeting. The oxygen pulses that supported their growth had pushed ecosystems closer to thresholds where more complex metabolisms could evolve. Each of these factors was a seed planted quietly in a world that still seemed fragile, waiting for the right conditions to bloom. When the Cambrian dawned, those seeds began to sprout. The higher oxygen levels allowed for shells made of calcium carbonate, sturdy enough to protect their wearers. Nutrient-rich sediments fed burrowers that carved through the seafloor, reshaping microbial mats and creating new habitats. The groundwork laid by the floods and their aftermath gave rise to ecosystems capable of supporting predators and prey, of driving arms races that rewarded innovation. The delicate balance of the Ediacaran world tipped into a new equilibrium, one where survival depended on adaptation rather than stillness. The fossil record reflects this transition. Ediacaran impressions fade, but just above them, in Cambrian layers, appear the first shells, burrows, and hard-bodied creatures. Trilobites with armored exoskeletons, worm-like animals with jaws, and predators with strange limbs and circular mouths began to populate the seas. Each of them depended on the oxygenated waters and nutrient-rich sediments that had been created long before, in the shadow of floods and storms. The Cambrian Explosion, then, was not a sudden miracle, but the flowering of seeds sown during the recovery from Snowball Earth. It is striking to think that catastrophe paved the way for abundance. The global ice, the melting floods, the oxygen surges, and the fragile Ediacaran communities all set the stage for the burst of innovation that would follow. Without them, the Cambrian seas may never have filled with such dazzling variety. The explosion of life was a delayed result, a culmination of forces building quietly over millions of years until the balance shifted and evolution accelerated. From this foundation, the story of life took on a new character. The world of quilts and fronds gave way to a realm of teeth and shells, of movement and conflict. Yet the seeds of that transformation were planted in silence, in the fragile experiments of organisms that absorbed nutrients from mats, and in the chemistry of oceans reshaped by floods. Their legacy lived on, not in direct descendants, but in the possibilities they unlocked. As the Cambrian unfolded, those seeds blossomed into the great tree of animal life, whose branches stretch all the way to the present day. The foundations laid by a drowned and alien Earth became the roots of everything that followed. The seas that followed the Ediacaran were no longer shaped only by chemistry and gentle growth. Something new had entered the stage, something subtle at first, but destined to transform life forever. In the quiet layers of sandstone that captured the final shadows of Ediacaran communities, scientists have uncovered faint traces of activity that speak of hunger and pursuit. Burrows winding beneath microbial mats, scratches etched into the seafloor, and disturbed sediments tell us that organisms were no longer content to simply absorb nutrients. They were beginning to feed on one another. The first hints of this shift are found in tiny tunnels carved through ancient sediments. These burrows, no thicker than a finger, meander through the beds where microbial mats once spread. Their makers were small, soft-bodied animals capable of moving through the sediment in search of food. By disturbing the mats, they could graze on the bacteria within or consume the nutrients trapped in the layers. These burrows are among the earliest signs of organisms actively modifying their environment, reshaping the once still seafloor into a dynamic landscape of disturbance and feeding. Other fossils preserve marks that suggest direct interactions between living beings. In some beds, Dickinsonia fossils bear faint, bite-like impressions as though pieces of their quilted bodies were scraped away. In others, trackways lead directly toward these soft-bodied organisms, hinting that mobile creatures may have crawled toward them to graze. These traces are not dramatic, not the tooth and claw encounters that would come later, but they are unmistakable signs that life had discovered a new strategy for survival, to feed on life itself. This was the beginning of predation, and its arrival would change everything. Once, the absence of predators had allowed organisms to grow large and soft, to spread across the seafloor without armor or defenses. Now, with grazers and feeders emerging, the stillness of the ecosystem began to unravel. To be alive no longer meant only to grow and absorb, but also to defend, to hide, and to adapt. Evolution had opened a new pathway, one that would lead to competition, innovation, and ultimately the explosion of diversity that defined the Cambrian. The fossil record of this transition is often subtle, but its significance is profound. Burrows cutting through sediments reveal more than movement. They reveal the stirrings of strategy. The organisms that made them were not drifting aimlessly, but seeking food with intent. Some burrows show branching patterns, as if their makers explored systematically, turning and probing through the sediment until resources were found. Others cut deeply, suggesting that animals had begun to mine the seafloor for hidden nutrients. This purposeful activity marks a turning point in the history of behavior. The marks on fossils themselves are even more striking. To see the outline of an Ediacaran organism with parts scraped away is to glimpse one of the earliest moments of direct feeding. It suggests that some organisms had developed the ability to rasp or tear at soft tissues, to extract energy from their neighbors. These early grazers were small and simple compared to the predators that would follow, but they carried within them the beginnings of an arms race that would drive life into new forms. The consequences of these new strategies rippled outward. Once feeding interactions began, the seafloor could no longer remain the peaceful quilt it had been. Organisms that had spread widely without defenses became vulnerable. Those that could anchor firmly, grow tougher, or reproduce quickly had better chances of survival. Those that could move with greater purpose had the advantage of reaching food first or avoiding danger. The balance of ecosystems shifted, pushing life into new directions. This was not yet the full Cambrian world of armored trilobites and swift predators, but it was the opening act. The hints of predation in these rocks are the earliest signs of ecological conflict, of interaction that went beyond coexistence. They reveal the moment when life stopped being passive and began to act upon itself, driving adaptation in ways that chemistry alone never could. It is remarkable to think that such faint burrows and shallow marks capture one of the most important shifts in Earth's history. They are quiet records of hunger, of organisms seeking not just sunlight or chemical nutrients, but each other. From these first stirrings grew the tangled web of predators and prey that would dominate the oceans for the next 500 million years. The stillness of the Ediacaran world was giving way to motion, to strategy, and to conflict, setting the stage for the full flowering of the Cambrian Explosion. And as these first ecological battles unfolded on the seafloor, The question was no longer whether life could grow, but how it could endure in a world where every creature might also become food. The creatures of the Ediacaran world left behind shapes that almost seem like riddles carved into stone. Their bodies appear as faint impressions pressed into ancient seabeds, delicate outlines of disks, fronds, quilts, and spirals. Yet when scientists try to place them into the great family tree of life, the branches seem to bend and twist away, refusing to fit neatly into any known category. These organisms defy comparison, standing apart from animals, plants, and fungi as if they belong to an entirely separate experiment in biology. The question of what they truly were has puzzled generations of researchers. Some scientists argue that they were early animals, soft-bodied forms that eventually gave rise to the diversity that followed. Creatures like Dickinsonia, with their ribbed and symmetrical bodies, seem at first glance to belong to the lineage of animals, perhaps distant ancestors of worms or other simple beings. Their growth patterns, preserved in the rock, show that they added segments over time in a way that feels animal-like. Yet, when chemical analysis was done on Dickinsonia fossils, traces of sterols were found, molecules that are strongly associated with animal tissues. This suggested that perhaps, after all, they were part of our distant kin. Other scientists see things differently. Some of these beings, especially the towering fronds like Charnia, seem more plant-like, standing upright and absorbing nutrients from the water around them. Their lack of mouths, stomachs, or digestive tracts makes them hard to imagine as animals. Instead, they may have lived more like giant leaf-shaped sponges or strange colonies, thriving quietly by pulling dissolved nutrients from the surrounding seawater. Still others propose that they might have been closer to fungi, sprawling across the seafloor in networks, feeding by breaking down organic matter. This fungal idea places them outside both the animal and plant kingdoms, in a lineage that feels both familiar and alien at once. There is even a more radical suggestion, one that sees the Ediacaran biota as something entirely separate from anything alive today. According to this view, they may represent an extinct kingdom of life, a branch that sprouted on the tree of evolution, flourished for tens of millions of years, and then disappeared without leaving descendants. If this is true, then the impressions in the rocks are not just the shadows of our ancestors, but of an entire lost experiment, a biological possibility that Earth tested and then abandoned. The diversity of their forms deepens the puzzle. Some appear like quilted mattresses spread across the seabed, their bodies covered in repeating geometric patterns. Others rise like branching fractals, splitting again and again into finer details, as though mimicking the mathematics of snowflakes or river deltas. A few look like coiled disks or radiating spirals, with no clear symmetry or structure that resembles anything known. In the absence of hard parts, their soft tissues left only vague impressions, making it even harder to decide where they belong. Part of the challenge lies in how they lived. Modern animals leave behind more than bones. They produce shells, teeth, or burrows that reveal behavior. The Ediacaran organisms left almost none of this. Their preservation as flat outlines suggests that their bodies were fragile, perhaps jelly-like, collapsing into the sediment when they died. Without skeletons, shells, or durable structures, their traces are little more than shadows in the sand. This fragility makes them hard to study and harder still to compare with the robust creatures that came later. The absence of modern equivalents only sharpens the mystery. Every living organism we know can be tied to a lineage that stretches back through time, yet the Ediacaran creatures seem to vanish without leaving heirs. They are not like corals, sponges, or algae, though they share faint similarities with each. They are not like jellyfish, though some had soft, disc-like shapes. Their unique forms remind us that life is not confined to familiar templates. In deep time, it can explore entirely different designs, some of which may succeed for millions of years and then fade away forever. This puzzle of classification has led to lively debate in paleontology. Some fossils are reinterpreted again and again as new evidence emerges. At one moment they seem animal, the next plant, then fungal, and then perhaps none of the above. Each new discovery adds another piece, but the picture never fully resolves. Instead, it becomes more complex, a reminder of how incomplete our knowledge of this era still island. The most haunting thought is that these beings may have represented a way of living that no longer exists. They absorbed nutrients in ways we struggle to imagine, grew according to fractal rules unfamiliar to our biology, and built ecosystems unlike any that followed. They were not failures in the story of life, but an entire chapter written in a language that is now lost. Their disappearance before the Cambrian Explosion left behind a silence, and in that silence, new forms arose that would eventually give rise to the living world we know. As the seafloor impressions whisper their riddles across hundreds of millions of years, they remind us that life has always been stranger, broader, and more experimental than the survivors alone can tell. And just as the last hints of predation were beginning to stir in their midst, these enigmatic beings stood as a final testament to a world that would never be repeated. For much of human history, the Ediacaran world lay completely hidden. The faint impressions of its strange organisms slept quietly in stone, pressed into ancient seabeds and sealed beneath layers of sand and mud. They were there for hundreds of millions of years, waiting for the right moment when a wandering eye and curious mind would finally uncover them. That moment came in the 1940s in the rugged hills of South Australia. A young geologist named Reginald Sprigg was surveying abandoned mines in the Flinders Ranges when he noticed something unusual in the rocks. At first glance, they seemed like simple ripple marks, the kind left by waves along a shoreline, but as he looked closer, he realized the patterns were too organized, too symmetrical, too deliberate. The rocks seemed to hold the outline of a living thing. Some were oval, with ridges running across their bodies like the folds of a quilt. Others stretched like leaves, with delicate shapes pressed into the sandstone. These were not just geological patterns. They were fossils, the preserved remains of life that had existed hundreds of millions of years earlier than anyone thought possible. At the time, the scientific world was not ready to accept what Sprigg had found. Many believed that complex life only appeared suddenly in the Cambrian Explosion, with little or nothing before it. When he presented his findings, his audience met him with skepticism. The idea that large, multicellular organisms had existed in the Ediacaran rocks of Australia seemed too radical, yet Sprigg persisted, and his fossils remained as silent witnesses, waiting for further discoveries to confirm their importance. Those confirmations came slowly, scattered across the globe like pieces of a puzzle. In the deserts of Namibia, paleontologists uncovered the remains of strange quilted organisms embedded in sandstone, so similar to the Australian forms that they could not be dismissed as chance. Across the frozen cliffs of Russia's White Sea, more impressions emerged, including delicate fronds that seemed to rise like underwater plants. In Newfoundland, along the rocky shores of Canada, entire bedding plains were discovered covered with fossils, vast fields of soft-bodied impressions, preserved as if a whole ecosystem had been frozen in place. Each new site added weight to Sprigg's claim. These were not isolated oddities. They were evidence of a lost world that had once flourished in shallow seas across the planet. As these discoveries spread, the story of Earth's history had to be rewritten. The simple view that life had been only microbial until the Cambrian suddenly gave way to something far stranger. The Ediacaran organisms proved that large, complex bodies had appeared tens of millions of years earlier than anyone expected. Their shapes did not fit neatly into the known kingdoms of life, but their presence could not be ignored. What began as a lonely discovery in the hills of South Australia grew into a global pattern, showing that the Ediacaran seas had been alive with beings we still struggle to understand. It took decades before this hidden chapter was formally recognized. In 2004, the International Union of Geological Sciences declared the Ediacaran Period an official part of the geological timescale. It became the first new geological period named in over a century, stretching from about 635 million years ago to 541 million years ago. For the first time, the lost world of quilted organisms, fractal fronds, and alien seafloor gardens had its own place in Earth's calendar. This naming was more than just a classification. It was an acknowledgement that life's story had a forgotten prologue, one that deserved its own chapter in the book of time. Even today, new discoveries continue to reshape our view of this age. Each fossil bed reveals new forms. Each chemical analysis sharpens our understanding of how they lived, and each comparison with modern life reminds us of how little we truly know. The impressions in stone that once seemed like mere curiosities now stand as evidence of one of Earth's most important transformations. They remind us that the past is never fully closed and that the deepest secrets of our planet can lie hidden in the quietest corners of rock. And so, from a quarry in Australia to the cliffs of Russia, from the deserts of Namibia to the coasts of Canada, the shadows of the Ediacaran have returned to light. Their rediscovery has changed not only our understanding of life's timeline, but our sense of what it means for evolution to experiment, to wander, and sometimes to take paths that lead to strange and fleeting worlds. If one could step back into the Ediacaran world, the feeling would not be of recognition, but of strangeness, as though the ground beneath your feet belonged to another planet. It was still Earth, but nothing about it resembled the familiar landscapes we know today. The continents were bare, stripped of life, nothing but ancient stone shaped by meltwater and volcanic fire. There were no forests to break the horizon, no grasslands to ripple in the wind, no birds to fill the sky with movement. Even the color palette was wrong. The seas shimmered in hues of green and red, painted by chemistry rather than coral reefs or flowering plants. The skies were heavy with storm clouds, and the air thick with gases that would make modern lungs burn. To walk to the shorelines would be to approach the true mystery. There, pressed into the shallow seafloor, lived organisms that seemed less like animals and more like living riddles. Dickinsonia stretched like oval quilts across the sediment, ribbed with neat ridges that looked designed rather than grown. Charnia rose into the currents like ghostly leaves, tall and fragile, swaying silently, though they had no roots and no stems. Rangomorphs branched out into fractal forests, repeating patterns that looked more like mathematical art than flesh. None of them had eyes, none of them had mouths. They carried no bones, no shells, and no hint of the familiar traits that animals later evolved. They absorbed nutrients directly from the water around them, as if the line between life and environment had not yet been clearly drawn. These creatures had no modern equivalents. They do not fit into the categories of animal, plant, or fungus, though they shared fragments of each. To see them would be to feel both awe and unease, as if confronted by beings that slipped through the cracks of classification. Their shapes looked simple at first, but the closer one examined, the more alien they became. Spirals pressed into stone seemed more like patterns left by currents than organisms, yet they pulsed with life once upon a time. Quilt-like mats sprawled over the seabed, stretching in great colonies, as if the very floor of the ocean had turned into a living carpet. The stillness of the ecosystem made it even stranger. This was a world without predators. No fish darted through the water, no claws grasped or teeth tore. Instead, these organisms spread outward slowly, filling the available space in silence. Growth was measured in patience rather than in conflict. The seafloor was a garden, but one with no gardeners and no competition, where beings unfolded like puzzles set down in the quiet. Even the geography of the time added to the sense of alienness. The continents themselves were not where we would expect them to be. Land masses were arranged in unfamiliar shapes after the breakup of Rodinia, and paleomagnetic studies show they drifted into positions that gave Earth a face it has never worn again. Mountains and valleys existed, but they were barren, untouched by roots or rivers. When rain fell, it carved fresh paths across stone, unsoftened by vegetation. When winds swept across the land, they gathered nothing but dust. The combination of landscapes and life created a world more dreamlike than earthly. Imagine approaching a coastline where red tides shimmer in the distance, where ghostly fronds sway beneath the water, and where the ocean floor is patterned with ribbed ovals and branching fractals that glow faintly in the filtered light. It was beautiful in its quietness, but also deeply unfamiliar. It is perhaps the only time in Earth's history when life seemed to be experimenting with forms that would vanish without leaving any descendants. Scientists call this the strangest chapter in our planet's story because it defies the usual rhythm of evolution. The Ediacaran world was a gallery of shapes and strategies that appeared suddenly and then disappeared just as suddenly, leaving no legacy except faint impressions in stone. They remind us that Earth has not always been a place of forests and animals, but at times has been something far more alien, where even the word creature struggles to find meaning. And as we turn from this quiet garden of riddles, the story begins to shift again toward the lessons this era left behind about survival, resilience, and the fragile balance of life. The Ediacaran world carries with it a lesson written not only in stone, but also in the very persistence of life itself. Before this period, Earth had endured one of its most brutal catastrophes. For tens of millions of years, the planet had been entombed in ice, its oceans locked away beneath frozen crusts, its continents smothered in silence. By every logical measure, the stage should have been cleared entirely. Life should have been extinguished. Yet when the ice relented and the floods poured across the continents, life returned not as a fragile echo, but as an explosion of creativity, filling the seas with shapes no eye would ever see again. It is here that we glimpse the resilience of life. Microbes hidden in sheltered environments, perhaps clinging to volcanic vents, salt pockets, or cracks beneath the glaciers, endured the long freeze. When the thaw came, they spread outward, seizing the nutrient-rich waters left behind by the floods. In their wake came the larger, softer-bodied organisms of the Ediacaran, creatures that seemed to arise from nothing, as if the earth itself had decided to try again. Their appearance reminds us that survival is not always about strength or speed. Sometimes it is about patience, about waiting in silence until the world offers another chance. This recovery was not gentle. The oceans they inherited were restless, full of chemical surges and shifting oxygen levels. One moment, conditions favored growth and abundance, and the next, they collapsed into scarcity. Organisms had to adapt to these wild fluctuations. They developed strategies that were unlike anything that followed, absorbing nutrients directly from the surrounding water, spreading themselves flat to capture resources across wide surfaces, or branching fractally to maximize contact with the environment. These adaptations were not permanent answers, but temporary solutions, fragile experiments in survival, and yet they worked, at least for a time. In this sense, the Ediacaran biota stand as a reminder of the power of adaptability. They were not armored like later animals, nor swift like fish, nor efficient like insects. They had no eyes to see or mouths to bite. Instead, they embodied flexibility in its purest form. They thrived in seas that were unpredictable, that shifted in color and chemistry, that pulsed with tides stronger than any we know today. Their very existence shows us that life can flourish not only in stability, but also in chaos. The near total extinction that preceded them makes their story even more remarkable. Earth had come so close to emptiness that it is possible complex life might never have arisen at all. The organisms of this age became the bridge between the microbial world and the Cambrian seas that would follow. Without them, there may have been no path forward, no gradual preparation of ecosystems, no quiet rehearsal for the burst of evolution to come. What is most striking is how alien their methods of survival were, yet how effective. Instead of competing with teeth or claws, they spread and absorbed. Instead of fighting for dominance, they endured by existing within the margins of possibility. In their stillness, there was strength. In their strangeness, there was success. They remind us that survival does not always mean triumph in the way we think of it today. Sometimes it means simply holding on long enough for the next stage of history to unfold. This resilience, written in the faint impressions left behind in sandstone, is a lesson that echoes forward into our own time. It tells us that life has weathered catastrophes far greater than any we know now, that recovery is always possible, and that adaptability is the greatest tool life has ever possessed. The Ediacaran seas whisper of a world that almost ended, and of the quiet persistence that ensured it did not. And as the story of survival unfolds, it leads naturally into questions of warning and reflection, for the same cycles of climate, oxygen, and adaptation that shaped their world still shape ours today. The Ediacaran age may feel like a distant dream, separated from us by more than 500 million years, yet its lessons press closer than we might expect. When the ice melted and the floods swallowed the continents, it was not a gentle change. The climate swung from frozen silence to sweltering chaos, from oceans locked in ice to seas that boiled with iron and ash. It is a reminder that Earth is not fixed or steady, but capable of transformations that feel sudden on the scale of life. To study these ancient transitions is to see how fragile the balance of climate truly is, and how quickly it can tip. The Great Freeze had trapped carbon beneath the ice, sealing gases away for tens of millions of years. When the thaw came, that carbon did not return slowly. Volcanoes poured it into the skies in vast amounts, and the oceans released what had been stored beneath the frozen crust. Carbon dioxide surged, and with it, the planet warmed at a pace that reshaped everything. Oxygen levels, too, shifted wildly, sometimes spiking to support larger bodies, sometimes falling and straining the organisms that had begun to grow. Life was not in command of these cycles. It was carried by them, lifted and dropped as if on a tide. The fragility of this system is written in the rocks. One layer tells of ice grinding across the continents. The next shows signs of floods, carving new scars. Still another carries the trace of oxygen rising and falling in unstable rhythms. Each shift left its mark, as if Earth itself was reminding future eyes that nothing in its climate is guaranteed. For the creatures living then, These swings were both opportunity and danger. In times of abundance, they spread and flourished. In times of collapse, they vanished without leaving descendants. Survival was tied to forces far beyond their control. Today, we find ourselves standing in a moment where carbon and oxygen cycles once again hold our future in their hands. We know that the gases we release into the atmosphere trap heat in ways not so different from the ancient pulses of volcanic fire. We know that oceans, like those of the Ediacaran age, absorb and store much of this excess until they can hold no more. The lesson from the flood world is that these systems may seem vast, but they are not endless. They can be pushed to breaking points, and when they break, the shift can be sudden. It is easy to imagine Earth as steady because it has carried us for so long, yet the truth is more delicate. A change in temperature of only a few degrees can tip the balance of entire ecosystems. A small rise in carbon can alter the chemistry of oceans. Oxygen, the invisible foundation of our lives, once fluctuated so drastically that whole groups of organisms disappeared. The fossil record shows that what feels permanent can unravel quickly. But there is also reassurance in the story of the Ediacaran. Life did not end with catastrophe. It adapted, it reshaped, and it continued into new forms. Even in the most alien of ages, where the seas turned red and green and the skies boiled with storm, life found a way forward. The warning, then, is not that the planet will fall silent forever, but that the conditions we rely upon are not guaranteed. Earth will survive in some form, but whether it remains a world for us is another question. The ancient flood world tells us that resilience is possible, but only through adaptation. It also tells us that the forces we shape today are the same ones that reshaped the planet then. Carbon, oxygen, water, and ice are the quiet engines of Earth's story, and when they move too far in one direction, the consequences echo for millions of years. To study this forgotten age is to be reminded that we live in a delicate balance, one that has tipped before and will tip again. And as this awareness settles, the story begins to turn toward how easily such lessons are forgotten, how this flood and its alien creatures slipped into obscurity, leaving only faint reminders in stone. When people think of great floods, they often turn to stories passed down through myths and scriptures, tales of waters rising and worlds being washed away. Yet the most extraordinary flood of all did not live in legend but in the very stones beneath our feet. It happened more than 600 million years ago, when the ice that had locked the planet for ages finally gave way. Vast torrents of meltwater surged across the continents. Oceans rose higher than at almost any other time in Earth's history, and the surface of the planet was transformed. It was a cataclysm far greater than any human story remembers, yet for reasons both simple and profound, most people have never heard of it. Part of the reason lies in time itself. Events so far removed from us are hidden behind layers of rock and silence. Unlike the later extinction of the dinosaurs, there were no bones to be found, no skeletons large enough to capture the imagination of a curious child. The creatures of this flood world were soft-bodied, fragile, and left behind only faint impressions, like shadows pressed into sandstone. For millions of years, their existence remained invisible. It was not until the middle of the 20th century that their traces were even recognized for what they were, and only in the early years of this century was the period officially named the Ediacaran. In that sense, this forgotten flood was hidden not just by time, but by our own lack of awareness. Yet if it is little known, its influence was immense. The melting of the ice sheets and the floods that followed reshaped every path life would ever take. The oceans became laboratories of possibility, Nutrients that had been trapped beneath glaciers spilled into the waters, fueling blooms of microbes and paving the way for larger, stranger forms. The chemistry of the seas shifted. Oxygen rose to new heights, and with that rise came the chance for complex bodies to grow. Without the flood, there may have been no Dickinsonia spreading across the seabeds, no Charnia swaying like ghostly fronds, no fractal gardens of Rangomorphs painting the ocean floor. These organisms were not just temporary experiments, they were the rehearsal for everything that would follow. By absorbing nutrients directly from their environment, they showed what was possible when bodies became larger than microbes. By spreading across the seafloor, they built the first communities of many species living side by side. By leaving behind their faint imprints, they etched into stone the proof that survival after catastrophe was not only possible but inevitable. The flood had cleared the slate, but life had written on it again in forms so alien that we still struggle to understand them. The hidden foundation of our world lies here, in this drowned chapter. The Cambrian Explosion, when predators and shells and eyes burst into being, could not have happened without the groundwork laid during this recovery. The balance of oxygen, the spread of nutrients, the first fragile ecosystems, all were forged in the aftermath of the floods. Even the shape of continents and oceans, carved by glaciers and reshaped by meltwater, set the stage for where life could take hold. What seems forgotten is in truth the beginning of everything familiar. To think of Earth's history as a book, this flood is one of its most important chapters, yet one of the least read. We walk across its evidence every day, in rocks that hold the scars of ancient glaciers, in stones that carry the whispers of vanished creatures, in the quiet patterns pressed into sandstone cliffs. The story waits patiently, recorded in the language of geology, even if most eyes pass it by. And as we step from this chapter into the final reflections, the realization lingers that this forgotten flood world was not only the origin of strange and alien forms, but also the beginning of the chain that would eventually lead to us. The story of the flood world may seem like a tale from another planet, a chapter where seas turned green and red, where creatures without eyes or mouths spread across the seafloor, and where the land was nothing but barren stone. Yet this alien world is not separate from us. It is not a curiosity locked in the past. It is part of us, woven into the very history that made our existence possible. The Ediacaran age, strange and fleeting though it was, prepared the stage for every living thing that would follow. Without those floods, without the strange experiments of life that crept into the oceans afterward, there may never have been the Cambrian seas, the forests of the Devonian, or the long reign of dinosaurs. Without them, there may never have been mammals or birds, or the human hands now turning these stones over and asking questions. To reflect on this time is to realize that life has always endured the unimaginable. When the planet froze solid, microbes clung to hidden places and refused to vanish. When the thaw unleashed floods that swallowed continents, life spread back into the seas and tried again. When oxygen rose and fell in unstable swings, organisms adapted, growing strange new forms that made the most of every chance. This quiet resilience is not just their story, it is ours as well. The blood in our veins carries oxygen only because ancient microbes once flooded the seas with it. The bones beneath our skin can exist only because earlier organisms dared to grow larger, testing the limits of what bodies could be. Even our presence here, thinking back on a world so far away, is the outcome of their persistence. There is something deeply calming in that realization. Life endures, life adapts, life thrives, even when the conditions seem unbearable. What we know today as Earth was built on the foundations laid in those forgotten oceans. The shapes of Dickinsonia, Charnia, and the fractal gardens of Rangomorphs may have vanished, but their legacy remains in the continued unfolding of evolution. They remind us that survival does not always look like triumph. Sometimes it looks like waiting in silence until the chance to flourish arrives. This is why the flood world, though little known, matters. It was not an ending, but a beginning, the bridge between emptiness and abundance, between a frozen silence and a planet teeming with complexity. To step softly through its story is to see how fragile Earth systems can be, but also how resilient life truly island. It whispers to us that change, no matter how violent or alien it may seem, can become the seed of something greater. As we close this journey together, I would love to know which part of this hidden world spoke most to you. Was it the quilt-like bodies of Dickinsonia, spreading across the seafloor like living carpets? The ghostly fronds of Charnia, swaying in the dark waters? The branching fractals of Rangomorphs, painting alien forests across the seabed? Or perhaps it was not one creature at all, but the reminder that life itself can endure catastrophe and return stronger than before. If you enjoyed drifting through this forgotten chapter of Earth's story, I would be grateful if you left a gentle like and tapped subscribe. It helps more curious minds find their way to this quiet corner where science and wonder meet to soothe and inspire. And if you feel comfortable, share in the comments where in the world you are listening from tonight. It is always humbling to see how far these stories travel, linking us together across different skies and different hours. Now, as we leave behind the strange oceans of the Ediacaran, let the thought linger that this alien world was never truly lost. It lives on in every breath of oxygen we take, in every cell that divides inside us, in every story of survival we carry forward. Life endured, adapted, and thrived, and in that continuity we find both comfort and wonder.